Good evening. Yeah, thank you. So for the past few days, we have seen different types of circuits. I mentioned that the op-amp has three modes of operation. The op-amp has three modes of operation. The first one is open loop configuration. So in open loop configuration, the application that we have seen is a comparator. That means op-amp inherently is not an amplifier. It is a comparator. It is going to compare V1 with V2. And if V1 is greater than V2, then the output is positive. If V2 is greater than V1, then the output is negative. And we have seen also how to calculate the duty cycle for the gate problem. The second class of circuits was negative feedback circuits. Negative feedback. In negative feedback, we had both linear and non-linear applications. We had both linear and non-linear applications. What are linear applications? In linear applications, we have seen simple adder, we have seen subtractor, buffer, Miller integrator, differentiator, and all the four types of amplifiers, which are V to V converters, V to I to V, and I to I. So all the four types of amplifiers we have seen: VCVS, CCCS, VCCS, and CCVS. And of course, we have also seen simple filters. So all these come under linear applications. But for non-linear applications, there was a need for us to introduce diode, right? Without diode, we cannot go for non-linear applications. In non-linear applications, we have seen rectifiers, peak detector, clippers, clampers, voltage multipliers, log amplifiers, exponential amplifiers. So all these come under non-linear application. So for that, we have introduced a diode, and we have seen simple diode problems. We have drawn the transfer characteristics, and then we realized that a rectifier has its own limitations. What is the limitation of a rectifier? That it takes a drop of 0.7. It takes a drop of what? 0.7 volts, right? So okay, yeah. So I was trying to say that we have seen the nonlinear application. So when we took up a basic diode, because we want to combine op-amp with diode, we realized that a diode takes a drop of 0.7, and we draw the characteristics. The output always trails the input by 0.7. The output is always less than the input by 0.7. So with that, we have seen rectifier, and especially peak detector with diodes had a lot of problems. For example, the ripple, whatever the loss that occurs when the diode is off, and if you see the law of conservation of charge, whatever the charge that is being lost for such a long duration is gained within a small duration. So when we look at the ripple, it's kind of very dangerous because the slope is very high in that ripple. So because of that large slope, the diodes pump in a large amount of current in that small duration. The size of filter capacitor should also be big. So we have calculated the ripple amplitude and all that. And finally, we said how we can completely eliminate the ripple. To completely eliminate the ripple, we have to see that the capacitor does not discharge at all. How can the capacitor does not discharge? If I isolate the capacitor and the resistor with a buffer. So then we went for precision circuits, right? So all these are rectifiers. We went for precision rectifier with op-amp, with the precision peak detector or the ideal peak detector. And all such circuits we have seen, and we try to improve them. So rectifiers, we have seen the passive rectifier and the active rectifier. The active rectifier are the precision rectifiers, right? Using op-amp. And peak detector, we have seen passive as well as active, right? But if you ask me what is the best rectifier known to us in the field of analog, I would probably say the one that is designed with differential amplifiers, right? So even rectifiers are finely designed with, it's not just the op-amp, even rectifiers are finely designed with the differential amplifiers, right? Okay, but we have seen basic rectifier, half wave, full wave, and then we combine them with op-amp with the diode. What was the problem with op-amp with a single diode? We had the saturation problem. Whenever the signal crosses zero line, when the op-amp suddenly switches from plus VSAT or to plus VSAT, there is a possibility that you might get distortion, right? So that sudden change might create distortion. So we even try to avoid distortion by connecting two diodes in the feedback path, and we always try to maintain the op-amp in the linear region. So we didn't allow the op-amp to go to saturation, right? So that was one thing. And then yesterday, we have seen the log amplifier and the exponential amplifier. So these are non-linear applications. We started off with comparator. We went for negative feedback, all sorts of linear applications. For non-linear, we had to introduce the diode, right? Without the diode, introducing diode and doing simple problems with diode, that is when you know the limitation of passive circuits. All the diode problems we have done initially are passive. They have no life in them, right? The diode always demands 0.7. The output is always trailing the input by 0.7. And it is the signal that has to drive that diode. Just imagine you have a signal that is less than 0.7 volts. Your signal is very small and it is less than 0.7, a 0.1 volt. What sort of diode is that which can rectify such small signals? So it's very difficult to have passive circuits. So whatever we have done for passive, the same thing we converted them into active, right? Using an op-amp, right? And somehow the clever idea is where you connect that diode. The diode has to be carefully put in the feedback path such that the op-amp blankets that diode. So 0.7 will be there, but the output will not be a function, will always be a function of input, and the output is never a function of that 0.7. So we have done problems with op-amp with diode also. And then of course, clippers, clampers we have seen, and the log amplifier and the exponential amplifier yesterday. And what are the last class of circuits? The last class of circuits are, the third one is positive feedback. Positive feedback. So yesterday I've introduced positive feedback circuits, and we have seen the bistable circuit, right? A bistable circuit or a flip-flop. This was designed by a person called Schmidt, is it not? So it's also called a Schmidt trigger. So if you give an input, which is above UTP, then it flips from plus VSAT to minus. If you give a trigger input, the input which is less than LTP, again the output is going to flip back to the original state. So there are two stable states at the output, either plus VSAT or minus VSAT. So we can call this as a bistable circuit. But there are other circuits also What if I want a relaxation oscillator? This is also called the astable circuit, the astable, right? Or relaxation oscillator. And the third one is the pulse generator, pulse generator. It's also called the monostable. Old books used to categorize them like this, but new books, they simply call it as a relaxation oscillator. So yesterday we have seen the Schmitt-Trigger or the bistable circuit. Now we are going to see the astable and the monostable. So that will give us some idea as to how to deal with op-amp, right? Op-amp in open loop, op-amp with negative feedback. Negative feedback includes both linear and non-linear applications. And then we have positive feedback circuits, right? In positive feedback, we have Schmitt-Trigger, which is bistable, and the other two categories we are going to see now. And you can collectively call them as some sort of multivibrators, right? So these are also called multivibrators, right? These are basically digital circuits. Okay. Multivibrators. So what is a multivibrator? It is a regenerative circuit. What do you mean by regenerative? A circuit with positive feedback. It is a regenerative circuit where the output of op-amp is either at plus Vsat or minus Vsat. Plus Vsat or minus Vsat. Based on the output state, based on the output state, they are classified as one, bistable. Bistable is also called a Schmidt trigger, right? What do you mean by bistable? If your input voltage, well, if it acts like a trigger, once you give a trigger input above UTP, it will go from logic 0 to logic 1. It will go from 0 to 1 or from 1 to 0, from one state to the other state. So it has two stable states. So what are the other names for bistable? You can call it Schmidt trigger. You can call it, in digital, we call it binary, or you can call it flip-flop. You can call it a Schmidt trigger or a binary or a flip-flop. So what is this flip-flop? From one state, it will go to another state based on your input trigger, right? The input that you're giving is the trigger input. Yesterday we have seen, right? And monostable. In monostable, what happens is, if you give a trigger, it will change the state, but it stays at this state for a small amount of time, and it comes back to the original state. So this is a pulse generator. This is what generator? Pulse generator. If you give a trigger, it will go from logic 0 to logic 1 or from 1 to 0. Either way, stays here. This is decided by RC components. This is decided by whom? RC values. And finally, it will come back to the original state. It will come back to the original state. Now, where are these circuits? Bistable, we know. I mean, bistable, we have seen that, by giving a trigger, how you are able to trigger input, how you are able to control the water in a tank, is it not? It's not just the water in a tank. Wherever there is noise, you can avoid noise in digital transmission, right? And the noise margin is called the hysteresis width, we have seen, right? And another example we can take for Schmidt trigger is, simple application is street light, is it not? Suppose you want the street light to glow only at night and the street light to be off during day, right? So you can fix one threshold for daylight and one threshold for night. But if the gap is very less, right? If you use a single threshold and there is no UTP and LTP, what happens if cloud comes? If cloud comes, naturally there will be obstruction of light, and naturally the voltage level will go down, and then it will start chattering. So you have to fix one for daylight, one for night. In between, even if the light intensity changes because of the clouds, which is noise, any unwanted signal is noise, the circuit will always be in the previous state. If it is off, it will be off. If it is on, it is going to be on. It is not going to change because of the arrival of clouds, right? So that is one method. But where is monostable used? Monostable, you give a trigger. I mean, now if you happen to go to any mall these days, or if you happen to go to McDonald's and you ask for a Coke, so what that guy will do, he'll take a cup, push the trigger and keep the cup. And after a stipulated amount of time decided by some value, RC values, automatically, now he's not using a tap these days, right? Just push it and then keep it. After some time, it is automatically, once it gets filled, which is already decided by some values, right? And then it gets automatically off. So it's something like this. So here it is logic 1. If you give a trigger, it goes to, from logic 0, it goes to 1. And here, the motor is going to get on here. When the motor gets on, it is on and on and on. But once the Coke gets filled, it is going to come back to the original state. So you can increase the RC values based on, this is for small RC, right? Small RC. What happens if you put a pulse like this? With a larger, then you can put a jug there. Are you getting? So you can increase the R and C values. The moment you increase the R and C values, then automatically the pulse is going to go larger. And I'll show you specifically in op-amp This is not RC, it is something like 0.69 RC. We're going to prove that. So it's 0.69 times of RC, right? So as the R and C values are increasing, generally we increase R, we don't increase C. C is fixed. If you increase the R value with a potentiometer, then automatically you can increase the pulse duration, right? Okay. So this is monostable. It has one stable state and one temporary state. This is a temporary state. We call it this temporary state in old books as quasi-state. It has one stable state and one quasi-state. So a monostable multivibrator is also called a pulse generator. Pulse generator. It is also called one-shot multivibrator, right? Pulse generator or one-shot multivibrator. So the first one is bistable. You give a trigger, it goes. Monostable, it goes to that state, stays there, and then come back. So this is a simple pulse generator. And what is this astable circuit? An astable circuit is nothing but a clock for digital circuits. So how do you build a clock for digital logic? A clock will look something like this. So this is used as clock for digital circuits. So you have a logic 0 and a logic 1 and a 0 and 1, but both states are temporary states, right? So it has two quasi states. It does not stay in one state for a longer period of time, just it keeps on going. This is nothing but, what are the names that you can give for this? This is a square wave generator. Square wave generator or square wave oscillator. Square wave oscillator, or you can call this as what? An astable circuit is a clock generator. Clock generator. Or any other name. See, it keeps on running freely. So some books call it a free running multivibrator. It's a free running circuit. See, it relaxes for some time here, and then it comes back and relax here. So it's going to relax for some time and then come down, relax. So it's a relaxation oscillator. It's a relaxation oscillator. So these are all synonyms for a square wave generator or a free running multivibrator, right? So it's a simple. Now, if you just go from 0 to 1, it's bistable. You come back, it's monostable. You keep going from 0, 1, 0, 1, 0, 1, that's astable. So there's nothing great in that. But all the values here are either plus VSAT or minus VSAT. Are you getting? Plus VSAT is logic 1, minus VSAT is logic 0. Now, what is the difference between a Schmitt trigger and an astable circuit, right? What is the difference between a Schmitt trigger and an astable? Schmitt trigger is a detector of square wave, whereas astable is a generator of square wave. So there's a difference between because there is no trigger input for astable, right? A Schmitt trigger, you have to externally give. It is not going to. You have an astable circuit based on the RC values. It keeps on giving 0, 1, 0, 1. Schmitt trigger cannot do that. For example, you give a signal, a trigger input less than, greater than UTP, and then you go and you go take a trip, right? So go somewhere, go to Delhi, and after 10 days you come, it still stays there, right? It always in the previous state. It cannot give you a square wave. When a square wave will come, you have to give two types of triggers, one greater than UTP, one less than LTP. In the course of detecting, it is going to give you a square wave. But if you don't give any trigger input, it will flip from one state to the other and just stays there. So Schmitt trigger is a detector. Schmitt trigger is a detector of square wave, right? So it's going to detect a square wave based on when you give a trigger, right? Whereas astable circuit is a generator of square wave. There is no need of you to give any trigger input. An astable circuit is a generator of square wave. So let me write here, no trigger required. So it is running freely. It's called a free running circuit, free running multivibrator, right? So Schmitt trigger cannot do that. The Schmitt trigger is totally at the mercy of the input trigger, right? So you give, it'll change. If you don't give, it can never give you a square wave. Okay. So first, let us build a free running circuit. So you don't have to have any external trigger. You just connect it and that's it. It's running freely, right? And then if you want, you can stop it after generating a single pulse. Then the astable can convert it into a monostable, right? So first we'll see the astable because you just switch on, it keeps on giving you a square wave. No need of any input. So this is basically an oscillator. It is a relaxation oscillator. So an oscillator does not need any input or a stable circuit. So yesterday we have given you some waveform, some random waveform, and the threshold was 3 volt, the other one was -3. We have drawn the waveform, how a Schmidt trigger can build a square wave output, right? You can observe the waveforms yesterday. Okay. Now, what is the function of this circuit? I told you in multivibrators, the output is always at plus Vsat or minus Vsat. And you cannot do beta N, beta P, V plus, V minus, because capacitor cannot change its voltage suddenly. So if your input voltage suddenly increases, that is reflected at V1, but your V2 is Vc, it does not change. When it does not change suddenly, because capacitor will not charge suddenly, it is going to charge slowly, there will always be Vd, which is a big number, either positive or negative. So your output will naturally be at what Vsat, either plus Vsat or minus Vsat, right? But instead of capacitor, if there is a resistor, what happens? If instead of capacitor, if there is a resistor, we have seen that if you connect 1 volt at the output and backtrack, if your V1 is greater than V2, then it is positive feedback. But if your V2 is greater than V1, it is what feedback? Negative feedback. Are you getting? But now capacitor is like a voltage source. It's like a voltage source. So if you try to short that voltage source here, right, and you realize that the V1 is always greater than V2, right? So your output is always going to be at plus Vsat. Okay. So let's do this case 1. Let V0 is at plus Vsat. Let V0 is at plus Vsat. Or we can take some simple values. We can take plus 10 and minus 10. What happens if this is plus 10? Or still simple 1K, 1K. So if V0 is at plus 10, because of voltage division, what is V1? What is V1? So V0 is at plus Vsat. What is V1? V1 equal to V0 into R2 by R1 plus R2. This is going to be 10 into 1K by 1K plus 1K. It is going to be how much? 5 volt. Your V1 is going to be 5. So if your V0 is at 10, now naturally with 10 volt at the output, the capacitor is going to charge. The capacitor is going to charge. From where? From 0, it is going to charge towards 10, right? V1 is at 5 volt here. V2 equal to Vc. V2 equal to Vc, right? Capacitor charges towards how many volts? Plus 10 volts. Capacitor charges towards plus 10 volts. So your V0 is 10, it is going to charge towards plus 10 volts. So what happens if this capacitor voltage, if your V2 just cross 5 volt? What happens if V2 cross 5? If V2 is greater than V1, or your capacitor voltage is greater than 5 volt, what happens? Then your VD is negative. VD is negative, and V0 switches from plus 10 volts to minus 10 volts. V0 switches from plus Vsat to minus Vsat. Are you getting? So very simple. Let me tell you, we don't know whether the output initially is at plus 10 or minus 10. If we assume the output is at plus 10, because it's a square wave, right? We are going to get a square wave. If you assume it is plus 10, within no time, it is going to switch to minus 10. How? With 10 volts at output here, V1 is going to be 5. Now this capacitor is connected to 10. So slowly the capacitor will charge to 1 volt, 2 volt, 3 volt, 4 volt, 5 volt. Once that capacitor voltage is 5.1, what is V2? V2 is nothing but Vc. So if your V2 becomes 5.1 and your V1 is at 5 volt, So 5.1 V2 is more than 5, VD is negative, your output will switch from plus VSAT to minus VSAT. So with no input, but in Schmidt trigger, what we've been doing, it has to wait when you'll apply a trigger. Here, nothing. You just switch on, automatically the state has changed from plus VSAT to minus VSAT. Are you getting? Now, please do the same case with assuming V naught equal to minus 10. What happens in case 2? Let V naught equal to minus VSAT or minus 10 volts. Tell me what happens now. If V naught is at minus 10, what is V1 by voltage division? V1 equal to V naught R2 by R1 plus R2. It is going to be minus 10 into 1K by 1K plus 1K. Am I right? It is going to be how much? Minus 5. It is going to be minus 5 volt, right? So your V1 is going to be minus 5. What is V2? V2 is VC. V2 is VC. V2 is VC. Now, in the previous case, where was the capacitor? The capacitor has charged till how many volts? The capacitor previously has charged till 5 volt. 5 volt. Now, suddenly your input has changed from plus 10 to minus 10. Your input has changed from plus 10 to minus 10. With minus 10, what is the new voltage here? Minus 5 volt. Now tell me, what is the source for the capacitor now? 10 became minus 10. So the capacitor has to charge towards minus 10. The capacitor has to charge towards minus 10. Minus 10. But what was the initial capacitor voltage? It was 5. Now it has to go towards minus 10. So what is the path for the capacitor? It will have to go towards the, always capacitor will reach its open circuited voltage. What do you mean by open circuit? If you open circuit the capacitor, the final value, V final of the capacitor, you are going to open circuit and see. When you open circuit and see, what is the final value of capacitor? The capacitor is going to reach towards how many volts? Minus 10. But will you allow him towards minus 10? We have to see, because now the path of the capacitor has changed, because when source changes, capacitor always want to reach the source. So V1 is minus 5, V2 is VC. If V2 is VC, now you tell me, what can I write? Capacitor charges, whether you call it charge or discharge, it doesn't matter. 5 volt is initial, final is minus 10. Capacitor charges towards minus 10 volts. Minus 10 volts. But what happens when this capacitor voltage has reached minus 5.1 volt? What happens when this capacitor reached minus 5.1 volt, minus 5.1 or minus 5? What will happen when it reached minus 5? This is minus 5, this is minus 5.1. What is VD now? VD is minus 5 minus of minus 5.1. VD is positive. Capacitor charges towards minus 10. When VC is less than minus 5, when your VC is less than minus 5, then your VD is again positive. V0 switches from minus VSAT to plus VSAT. V0 switches from minus VSAT to plus VSAT. Are you getting? So same thing. We have just repeated what we have written here. First with positive values, in the next case with negative values. That is the only difference. First I started with 10. So now tell me, with 10 volts at V0, V1 is 5, capacitor is reaching towards 10. When it's reaching towards 10, 1, 2, 3, as 1, 2, 3, VD positive, VD positive, VD positive, VD positive. Once V2 reached 5.1, then VD became negative because inverting voltage is greater than non-inverting. The output flipped from plus Vsat to minus Vsat. In second case, what happened in second case? If the output is at minus 10, then the new voltage, the new threshold here. So in Schmitt-Trigger, what did we call this 5 and minus 5? This we called it UTP. Do you remember? This we try to call it as what? UTP. And this we are trying to call it as what? LTP in a Schmitt-Trigger. Do you remember? Suddenly the voltage has changed to minus 5. Now there is no input. Capacitor itself is the input now for us. In a Schmitt-Trigger, it was at the mercy of the input. When input will come, when the tank will get filled. I will use tank water for 5 days. You will use it for 10 days. Another will use it for 1 day. So the Schmitt-Trigger is always at the mercy of input. When can I detect a square wave? Are you getting? But here, no. Capacitor is in the place of the input. Is charging from the output port, right? So slowly the capacitor will reach towards minus 10 from the initial point when the capacitor voltage is less than minus 5. Why it is less than minus 5? Remember, above UTP the capacitor should charge, below LTP the capacitor should charge. That is when the Schmitt-Trigger output is going to go from plus Vsat to minus. So now the capacitor will reach towards minus 10. In that travel, he will encounter minus 5. So once he touches less than minus 5, that is when the output will flip from minus Vsat to plus Vsat. So whatever I'm telling you, you can always support this with a good waveform. Sidnat, you can always support this discussion with a good waveform. So what is a waveform? What is V0? V0 is at how many volts? Plus 10 initially. When V0 is 10, it is relaxing here. What is your capacitor voltage? Your capacitor VC, what it is doing when this is at 10? Capacitor is charging towards 10. Capacitor is charging towards 10. Is charging towards 10. Towards 10. But when this capacitor touches 5 volt, when the capacitor touches how many volt? 5 volt, what will happen to the output? The output will switch from plus Vsat to minus Vsat. The output will switch from plus Vsat to minus Vsat. Minus Vsat. Now the capacitor is confused now because the source is changed. The source is changed. The source was 10, suddenly it became minus 10. Now the capacitor will think, okay, now I have to charge towards minus 10. Previously, he was charging towards 10. Now he has to charge towards minus 10. So now he's going to change his direction towards minus 10. But when he encounters a voltage less than minus 5, again your VD becomes positive here, and the output will flip from plus Vsat to minus Vsat. So this is the capacitor voltage. So this is the time period T. And because the RC values are same, it's going to be T by 2. So what is this plus 10? This plus 10 is nothing but plus Vsat. Minus 10 is minus Vsat. What is this here? Vsat into R2 by R1 plus R2. And this is minus Vsat into R2 by R1 plus R2. What happens if R1 and R2 are same? Then if you have 10 volt at output, you're going to get minus 5 volts, right? Okay. Calculation of frequency. Now, if you allow it for an infinite time, where will the capacitor reach like this? Maximum it is going to reach what? Plus Vsat. Am I right? So this is initial, and this is final, right? Initial, final. But after T by 2, the circuit is going to take over. It's going to flip that, right? From plus Vsat to minus Vsat. Once it touches a voltage, Vsat into R2 by R1 plus R2. Okay. But before that, first we will find the paths. We'll have to find the path from the initial to final. So what is Vc for all time? V initial minus V final e power minus T by Rc plus V final. V initial is minus Vsat into R2 by R1 plus R2. V final is Vsat e power minus T by Rc plus Vsat. This is capacitor voltage for all time. Let me check whether I've done it correct or not. What if I put time t equal to 0? Just put time t equal to 0. What is e power 0? E power 0 is going to be 1. Minus Vsat plus Vsat gets cancelled. You are at the initial point here. Okay, correct. Let me substitute t infinite. If I substitute t infinite, e power minus infinite is 0. So this whole term gets cancelled. You are going to have only Vsat here, right? So this whole term here is going to get cancelled. That's fine. So we know the path now. But I don't want a 0 or infinite. I want t by 2. So at t equal to t by 2, the capacitor is going to land at V sat into R2 by R1 plus R2. V sat into R2 by R1 plus R2. So let me substitute. Therefore, V sat R2 by R1 plus R2 equal to, let me take minus V sat common here, R2 by R1 plus R2 plus 1 minus V sat plus V sat here. So V sat is for minus t by 2 RC. Right, so t is t by 2. Let's cancel V sat. 1 plus R2 by R1 plus R2 into e power minus t by 2 RC. 1 minus R2 by R1 plus R2. R1 plus R2 in the denominator gets cancelled. E power minus t by 2 RC equal to, what is numerator in the right side? It's R1. The denominator in the right side numerator goes to the denominator. It's R1 plus 2R2. So if you apply log, t is going to be minus 2RC log R1 by R1 plus 2R2. So this is going to be the time period. This is going to be the time period. So first we got the capacitor is charging in some exponential fashion. There is no virtual ground, so don't put linear and all that. There's no virtual ground and positive feedback. So the capacitor is charging in a linear fashion. And then after a time t equal to t by 2, he lands up at V sat R2 by R1 plus R2. By substitution, you get t is minus 2RC log R1 by R1 plus 2R. So this is the calculation of frequency. So I took this duration here, right? This one. So the good thing about this circuit is there is no input for it, right? There is no input. It is a generator of square wave. It just keeps on generating square wave based on the R and C values, right? So this is the calculation of frequency. Now this is an old gate problem. If you remember the formula, you can directly substitute. It says that find time period. Find the time period of the square wave, right? The old gate problem. Find the time period of the square wave. So 4 options were given in the gate problem. The options are 2 tau log 1, 2 tau log 2, 2 tau log 3, 2 tau log 4. 2 tau log 1, 2 tau log 2, 2 tau log 3, 2 tau log 4. So these are the 4 options, right? So how do we solve this? Right, so what is T? We know that T is minus 2 RC log R1 by R1 plus 2R2. Am I right? So see, that is why these type of questions, these in the present day, we don't get, because a student has to remember the formula, is it not? So such type of questions these days they are not giving. So then and there you have to do some calculation within 1 or 2 minutes. So these type of questions are asked. Old gate problems, if you see, when we were writing gate, we had to remember even formulas. So that's a headache. So let R1 equal to R2 equal to R. Then what do you get? Let R1 equal to R2 equal to R. Then T is minus 2 RC log R by R plus 2R. It is 1 by 3. So because there's a negative sign, I can write it 2 tau log 3. All right, 2 tau log. There's a negative sign. Please see here. Time period cannot be negative. 1 by 3, is it not? So it is 2 tau log 3. So this is an old gate problem for 2 marks. So in the present day, these type of questions are asked. Now we all know what is the output. The output has only 2 levels. What are the 2 levels of output? Either plus VSAT or minus VSAT. So the gate examiner has given some voltage here, say plus 12 and minus 12. I don't remember exact numbers, but circuit is same. This is a gate problem, but values I don't remember, so I'm just changing them, right? 12 minus 12. So some values I have given. and the examiner, he wants you to calculate V1. He wants you to calculate V1, right? So simple question. We know V0, the shape of V0 and the shape of V1 both are same, because a resistor divider will never change the shape. Of course, capacitor voltage is different, but V1 is the attenuated portion of V0. It's just a decreased waveform of. If V0 is a big square wave, then V1 will be a small chota square wave. Are you getting? Chota square wave. It's just a reflection of V0 is V1, right? But how much it is going to get attenuated, we will have to see now, right? So this is also a gate problem. Now what happens if V0 is at plus 12? Let V0 equal to plus 12. Plus 12. So which diode is on? Which diode is on, D1 or D2? D1 on, D2 off, V0 plus 12, D1 on, D2 off, V1. So what is V1? V1 equal to V0 into 1K by 3K plus 1K. Am I right? So 12 by 4. It is plus 3 volts. So if you have V0, a big 12 volt square wave, your V1 is going to be 3 volt, chota square wave, right? So V1 is 3. What happens if V0 is at minus 12 volt? If V0 is at minus 12, D1 off, D2 on. So the path is this. V1 is V0 into 1K by 1K plus 1K is minus 6. All right. So V0, what is the sketch of V0? Plus 12 and minus 12 V0. What is the sketch of V1? Sketch of V1. Tell me. If V0 is at plus 12, your V1 is at plus 3. If V0 is minus 12, it's going to be minus 6 plus 3 minus 6. So you V0, 4 options were given, right? Different square wave and exponential signals like that. So your V1 is just going, we know that this is an astable circuit, and we know that the output is going to be what? Some square wave with some time constant RC, and the 2K and 1 microfarad is not needed, right? Just simple for time pass he has given, because his aim is only to sketch V1, right? So how do we sketch V1? If you know V0 is a square wave between plus 12 and minus 12, then your V1 is going to be a reflection of that, right? And please mind you, in the gate exam, he said diode ideal, right? Op amp and diode are ideal. Op amp, diode ideal, right? So when diode is ideal, it is replaced by short circuit in forward bias, right? So your V1 is a chota square wave, it's a small square wave which shuttles between plus 3 and minus 6, right? So this is a gate problem for 2 marks. Sketch V2. Op amp and diode ideal. So sketch the capacitor voltage. So your V2 and VC both are same. So what can we take power supply? Power supply I have not given. Thank you. Some students in the comment section commented rightly. They are saying that, sir, you have not given plus VSAT and minus VSAT. That's true. I stand corrected. So plus 12 and minus 12 are the plus VSAT and minus VSAT. So now it will be easy for you to sketch the waveform. Good. So tell me, let V naught is at plus 12. Your D1 is on. If D1 is on, what is your V1 here? If D1 is on, V1 is going to be 12 into 12K by 36K plus 12K. So it's going to be plus 3, all right? So let V naught is at minus 12 volts. D2 is on. So what is V1 here? V1 is going to be minus 12 into 12K by 60K plus 12K. Going to be minus 2. So what should be the output? We know that the output is either plus 12 or minus 12. The output is either plus 12 or minus 12. Now, if the output is at 12, what is V1? What is V1? It's going to be 3. Now the capacitor will charge towards 3, will charge towards 12, but after he touches 3 volt plus, when V2, this is 3 volt, when this goes 3.1, the output will flip from plus 12 to minus 12. Now, the capacitor should reach towards minus 12 because with minus 12, the new voltage is going to be minus 2. So the capacitor has to reach towards minus 2 here. And then plus 3. And then minus. So this is the capacitor voltage waveform, right? V1. This is V1. Right? And you have V0 here. So sketch V1. The V1 is going to shuttle between 3 volt and minus 2 volt. Right? This is V1 or V2. Sketch V2, V2, V2. This is V2. What is V1? V1 is a non-inverting voltage, that is a square wave, is it not? This is V2. Sketch V2 is the question. Now find the time period. This is an IES problem for 10 marks, but directly we'll write the answer because already we have derived. So this 10 marks question, we directly write the answer. So R1, R2. So RA and RB. Right. It says find the time period. Diode is ideal. Diode is ideal. This is D1 and D2. Now the waveform is same, but the time constant has changed. In the previous case, the charging time constant or discharging time constant, whatever you call it, when it goes up and down, it's always RC. But now it has RA into C when the output, when D1 is on, when the capacitor is going, when it is charging in this direction with time constant, RA into C. When it is discharging in negative, because D2 is on for V0 negative, so it is RB into C. That is the only difference. And because we have already derived it, we can just write the answer, right? So what is the answer for this 10 marks question? So the waveform is like this, all right? The waveform is like this. The thresholds are same. The thresholds are same. It is from minus R2 Vsat by R1 plus R2. It has to reach towards Vsat. And this duration, we'll call it T1. This duration, we'll call it T2. The only difference is this voltage is Vsat. It has to stop at Vsat into R2 by R1 plus R2. So the threshold is same. Threshold is always same. But the rate at which it has to charge is changing. Now, this charging time constant, what is tau 1? Tau 1 is going to be, what is tau 1? It is going to be RA into C. And tau 2 is going to be RB into C. RB into C. So what is the answer that we got previously? We said T equal to minus 2RC log R1 by R1 plus 2R2. Do you remember? Right? Why that 2 has come? Because we took T by 2. Now, let us take half T1. Then it will have minus what do we get? Minus 2RC. Now, minus RA into C log R1 by R1 plus 2R2. So you see the first derivation we have done. T2 is going to be minus RB into C log R1 by R1 plus 2R2. Am I right? So what is the total period? The total period T is going to be T1 plus T2. So this is given for 10 marks. You can derive it. Already we have done the derivation. Only difference is in the tau value, right? Instead of putting RC, there is RA into C in this path and there is RB into C in this path, right? So now T1, T2 are not same because the tau values are different. The rate at which it is charging. See, simple. What is the relationship between time, distance, and speed? What is the relationship between the time, distance, and speed? Distance is equal to speed into time. Or what is time? It is distance by speed. So the time T1 is decided by two factors, the distance and the speed. Distance is R2 VSAT by R1 plus R2, 2 VSAT R2 by R1. So R1 and R2, the two thresholds, will tell you the source and the destination, right? The distance. But how, at what rate it should charge there, right? So suppose here, I'm having point A to point B. There are so many ways of reaching this voltage to this voltage. So somebody would reach like this quickly for this small duration. Somebody would say, okay, at the same voltage, I will reach like this and the duration will change. Somebody will take more time. Are you getting? But distance is the same. Distance is from point A to point B. But do you want to quickly reach or slowly reach? So it's decided by whom? The speed is decided by RC. So it's a simple logic that my time is a function of distance and speed. Are you getting? Distance and speed. The speed is decided by RA into C, but the distance is decided by R1 and R2. The R1 and R2 are going to decide the distance, right? Remember. Okay. Now, what if here we have another two diodes? Then you can take this as a homework and try to solve this. So what if I give 4 diodes, right? So this you can solve as a homework. So how do you calculate the time period? So someday in IES you can expect this question, right? Maybe for 15 marks or something like that, 10 marks. So it's simple. You can do it provided you know the sketch. But when after you know the sketch, you can take the initial value and final value, and then you can substitute to get the answer, right? So what sketch are you going to draw? What is the sketch that you're going to draw? V naught goes between plus Vsat and minus Vsat. Am I right? Minus Vsat. So tell me, what is your VC? What is your VC sketch, your V2? Because if you know V2, then you know how to calculate the period, right? So if my output is at plus Vsat, who is the one who's deciding the threshold? If the output is at plus Vsat, it's going to be Vsat into, what is this voltage here? It's going to be Vsat into R1 by R1 plus R3. Am I right? So the capacitor should reach this value. What is the value here? Vsat into R1 by R1 plus R3. Am I right? And with what time constant it has to reach? This one. The upper diode D3 is on, so it's going to be RA into C with that time constant. But once it crosses this voltage, V2, it crosses that threshold, the output flips from plus Vsat to minus Vsat. And what is the new threshold here? The new threshold here is going to be what value? Negative means minus Vsat into R1 by R1 plus R2. So it has to reach from here a value lesser than this value, which is minus Vsat into R1 by R1 plus R2. But at what rate the which diode is going to on? It's D4 is going to be RB into C. Okay, and now again this path is still here. So this is the, oh, I said this is homework and I did it, right? So this is what happens. Fine, that's the homework problem, and I've done it. I've done it sitting in my home, right? So you calculate the T1 and T2, right? So you can calculate T1 and T2, right? So this is T1, you can calculate T2. And what is the total period? The total period is going to be T1 plus T2, something like that, right? Okay, so someday in IES they can expect this question also. So in this duration, who is getting on in this duration? Which diodes are on here? RA into C, T1, T3 on. And which diode is getting on in this duration? It's T2 and T4 on. Right? Okay, so this is about the stable circuit. It's a square wave generator. You can use it, the output, you can use it as clock for digital logic. And now we know how to change the time duration also by changing R1 and R2 values. And we also know how to change the rate at which it has to reach that point. That is decided by R and C values. The speed is decided by RC, but the distance is decided by R1 and R2, right? And what is the last one in the multivibrator? The positive feedback circuits, the last category is the monostable, right? Monostable or pulse generator. Monostable or pulse generator. Okay. So this is an astable circuit we have already drawn. So this is how we started, is it not? I said this is R1 and this is R2, P0 plus Vsat and minus Vsat. Am I right? Let me show you. This is how we started, right? Yeah. So this is the one we started, right? We took plus 10 and minus 10. So what is the function of this circuit? Once again, if output is at 10, then V1 will be 5. The capacitor will charge towards 5. Once the capacitor reaches more than 5, the output will, VD will become negative and output will flip from plus Vsat to minus Vsat. Now, if it flips, how can I get a stable state? Because for a pulse generator, it should always be either at logic 0 or logic 1. If you give a trigger, then it has to change the state. But here, there is no one to change. It keeps on changing plus Vsat, minus Vsat, plus Vsat, minus Vsat. So we have to stop him, right? How can I stop him? For the same circuit, at V2, can I connect a diode across the capacitor? What happens? If I connect a diode across the capacitor. And what happens if the diode gets on? Finish, the capacitor is gone. The diode says that capacitor, you have to maintain only 0.7 volts. So V2 is going to get restricted at 0.7. So your 5 volt is always greater than 0.7. The output will never change state. It is going to be stable. It is waiting when you will give a trigger. Because if you give a trigger, then only the pulse generator should work. So the pulse generator should wait for you, right? It's not like you switch on the machine and the coffee keeps coming. When the coffee comes outside, when the coffee will fill, when you're going to fill Coke, first customer should come. Yes or no? So if there is human intervention, when you give a trigger, that is when the state has to change. You should not keep on changing above 5, below 5, above 5, below. No, right? We have to stop him to set up a stable state. So to set up a stable state, what is the change that I'm going to make in this circuit? The change is that I will put a diode here, a diode. So what happens if you put a diode? Oh, yeah, because I've shown you the previous circuit, same voltages will take plus 10, minus 10 for simplicity, 1K, 1K, right? Is this a diagram we took, right? Yeah. Now tell me, let V0 is at plus Vsat. Let V0 is at plus Vsat, right? which is plus 10, right? Then what is V1? This is V1. This is V2. V2 is VD. V2 is VD or VC. All are same, right? V2, VD, VC, all are same. The capacitor voltage and the diode voltage are same, right? Parallel connection. So if V0 is at 10, your V1 is at 10 into 1K by 1K plus 1K. It is plus 5, right? So with 10 volt at output, what will happen if with 10 volt here, what will happen to the diode, right? So let me draw here. I have a 10 volt supply connected to R, and there's a capacitor and a diode. Now what will happen if you directly give a plus 10 volts to anode? The voltage here, V2, is going to get restricted to 0.7 volts. The diode is on, the voltage is going to get restricted to how much? 0.7. So with 10 volts at output, the diode is forward bias. The diode is forward bias, and V2 equal to VC equal to VD on equal to 0.7 volts. Is going to be 0.7. Now tell me, V1 is 5, VD is 0.7. What is the difference VD? Okay, this I'll put capital D just to differentiate between the op amp and the diode drop, right? So what is VD of the op amp? It is going to be V1 minus V2. It is 5 minus 0.7. 4.3. Oh my God, that's a big voltage. 4.3 is a big voltage difference, and the gain of an op amp is in lakhs. So your V0 stays at plus 10 volts, right? It stays at plus 10 volts. This is the stable state. This is the stable state. So now nothing is going to change. The output is restricted to 10 volts. When you switch on, V0 is at 10, V1 is at 5, diode is on 0.7, the VD is going to be 4.3. So the output stays at 10 volts. So this is the stable state. This is the stable state. So V0 is A times of VD, right? V0 is A times of VD. So your V0 stays at plus V set, right? Okay. Fine. Now, this is before trigger, right? This is before giving trigger. before giving trigger. So this is the stable state. Now let us give trigger. Now where shall we give trigger? So we have a capacitor here, a diode here. Now what is a trigger? A trigger is a sudden voltage that you give for a short duration so that the output will flip from plus Vsat to minus Vsat, right? So this is 1K, 1K. So here, the voltage here is restricted to 0.7. Now tell me, how much voltage should I give here? How much voltage should I give here so that the output will switch from plus Vsat to minus Vsat? The output should switch from plus Vsat to minus Vsat. What voltage should I give to the non-inverting terminal? If you want to switch to minus Vsat, the non-inverting voltage should be less than how many volts? 0.7. So this should be less than 0.7. Or some books say that you can give a negative trigger like this. You can give some negative trigger, right? That's what they say. But this negative trigger, how do we generate this negative trigger? From where do we get this? What I feel is you can directly connect a switch to ground, right? You can directly connect a switch to ground. But if you directly connect, what's the danger? Just suddenly you close it, that the point is directly connected to the ground. So what is a device that will oppose the sudden change so that the chance of getting a spark you can avoid? Capacitor, right? So you can have a 100 microfarad capacitor like this, so you can just put a capacitor in series and then close it. When you close it, suddenly this point V1 is pulled directly to how many volts? 0 volts. All right. So your problem is solved. But what is the danger if you have a capacitor? First customer comes for coffee, you gave a trigger, second customer, third customer. What if this capacitor also charges to 0.7? Then maybe it will work for 2-3 customers, and after that, even if you keep giving trigger, the capacitor has a voltage more than 0.7, so the output does not change. So you might provide a discharge path here, a small discharge path, right? So what happens? This is a push button switch. So you just close that switch for a short duration. You give a trigger input, and this point is pulled down to ground. So this is the external trigger circuit, right? So this is a trigger circuit we used to use, in X-ray machines and all that. When I was working for Wipro, we had a trigger hand switch. The radiographer used to have. When you open that hand switch, there's a capacitor in parallel with a resistor and a contact switch there, right, for a short duration, like that. Okay, right? But generally textbooks say that you have to have some sort of a differentiator or something like that, right? So get negative trigger, but it doesn't matter. Fine. So let us give trigger. The second case is let us give trigger for a short duration. So the moment you close the switch, what will happen to V2 or V1? V1 for a short duration is almost how much? 0. V2 is at 0.7. Your VD is negative. When your VD is negative, your V0 switches from plus Vsat to minus Vsat. So now it has changed from plus Vsat to minus Vsat. When you apply that switch for a short duration, right, just close it like that, right? Okay. But if you don't have a capacitor, then also is okay. But just when it comes in contact, suddenly that point is pulled down to ground, right? So it's better whenever you are decreasing that voltage. So somebody should be there to oppose that change. But the good news is capacitor does not allow sudden changes, but it cannot avoid the change, right? It cannot avoid the change. So There will be a change. We'll try to oppose it, right? We'll try to oppose it. So V naught switches from plus VSAT to minus VSAT when you apply that switch. Now tell me, with minus VSAT at output, with minus VSAT at output, the diode, what will happen to the diode now? What will happen to the diode? The diode is reverse bias. The diode is reverse bias. Reverse bias. And capacitor charges towards minus VSAT. Towards minus VSAT. Towards minus VSAT. Now tell me, after trigger, what are the numbers now after trigger? After trigger, your V1 is going to be minus VSAT into R2 by R1 plus R2, which is minus 5. And your capacitor V2, VC equal to V2, charges towards minus 10, right? Minus 10. So when it charges towards minus 10, when V2 is lesser than minus 5, your VD again becomes positive and V0 switches from minus VSAT to plus VSAT. So that means a monostable multivibrator is doing only half operation of the S-table. Is doing only half operation of the S-table. Are you getting? So S-table, what it used to do, plus VSAT to minus VSAT, minus VSAT to plus VSAT, plus VSAT to minus VSAT, minus VSAT to plus. But look at this fellow. Case 1, we changed it by giving a trigger. You just gave a trigger, first case is over. Now second case is done by the circuit. Who is doing first case? First case, human intervention, we have changed it. Then it flipped from plus VSAT to minus VSAT. It made the diode off. When it makes the diode off, the capacitor has to charge. The capacitor has to charge towards what value? Minus VSAT. It has to charge towards minus VSAT. But in that due course, when this voltage is minus VSAT, this is at minus 5. When this is at minus 5.1, then what is the difference? Minus 5 minus 5.1. The difference VD is 0.1. The output will flip again from plus VSAT to minus VSAT. Now, how can I convince you the whole story here with a waveform? Without a waveform, it is difficult to contemplate the whole scenario, right? That is why waveforms are important. VC. What is VC or V2 or VD? Your VC is your VD. Tell me, when your V0 is at plus VSAT, your VD is at 0.7 volts. It is at 0.7 volts. And we know that the diode is on initially. At this duration, you give a trigger. At this duration, you give a trigger. Now the capacitor, when you give a trigger, what is happening to the output? It has to reach minus VSAT. But when it reaches a voltage, okay, I'll make it still simple. R1 equal to R2. If R1 equal to R2, this is going to be minus VSAT by 2, half. And what is your V0? Your V0 initially is going to be at plus VSAT till here. And then it will fall down to minus VSAT. And stays here till you cross minus VSAT by 2. So once you touch plus VSAT, again the diode is what bias? Forward bias. Again the diode is forward bias, right? So this is the pulse width. This is the pulse width. Okay. So by looking at this waveform, let me explain this circuit once again. Right? Let me explain this circuit once again. Right? See here. Tell me. Initially, the output is at plus VSAT. V1, if it is at plus VSAT, say plus 10. This is at plus 5. your V1 is at plus 5, and the capacitor wants to charge towards 10. But the moment you give 10, the diode is on, the output is restricted to 0.7 volts. The output is restricted to 0.7 when this is at 10. This is the capacitor waveform. Now, what happens when you close this switch for a short duration? Your V1 is pulled down to ground, 0. Your output will flip from plus VSAT to minus. When it flips to minus VSAT, the capacitor wants to reach towards minus 10, minus VSAT towards minus 10. And when it encounters a voltage less than minus 5, again it is going to flip to plus VSAT. Are you getting? I think this space is not enough for me to calculate. So I will use this calculation of pulse width. Calculation of pulse width T, right? So this is 0.7 volt approximated to 0. And this voltage is minus VSAT by 2. And the final value is minus VSAT. Minus VSAT. This is the capacitor voltage for all time. This V initial is going to be V final, right? And this duration is your T. So tell me, what is capacitor voltage for all time? V initial minus V final, e power minus T by RC plus V final. It is 0 minus of minus VSAT, e power minus T by RC minus VSAT. Or it is VSAT into e power minus T by RC minus 1 is capacitor voltage for all time. Am I right? Now, after a time t equal to capital T, the capacitor lands up at minus VSAT by 2. When it will be half if R1 is equal to R2. If R1 is equal to R2, then it is going to land up here. So therefore, minus VSAT by 2 equal to VSAT into e power minus T by RC minus 1. So VSAT gets cancelled. E power minus T by RC is 0.5. What is natural log of 0.5? What is natural log of 0.5? What is natural log of 0.5? Anybody with a calculator? What is natural log of 0.5? Good. So your T is going to be 0.693 RC. This is the pulse width. I think you remember this, very, very popular equation in your lab records. Yes or no? So what is the pulse width of a monostable a multivibrator? It is 0.693 or 0.69 RC. So this is very, very popular, 0.69 RC. So after 0.69 RC, automatically it will come back to what state? Original state. So here, where the design what we made is from plus VSAT to minus VSAT and stay at minus VSAT. You can do in the other fashion also. Let initial be logic 0 minus VSAT. Once you give a trigger, it will go to plus VSAT, stay for some time and then come back. Are you getting? And then it is going to stay here forever in the stable state. So it has one stable state and the other quasi state. So till here, the diode is on, and after that, the diode is off, and then the diode again is on. The diode is again on. Okay, so let me explain this one last time. When you switch on, let the output is at plus 10. V1 is going to be plus 5. Diode is going to get on. The diode is on here. V1 is greater than, your V1 is plus 5. Phi is greater than 0.7. The output continues to be at plus VSAT, plus 10. So this is the stable state. How are you going to change the state? To change the state, your V1 should be less than 0.7 or V2 should be greater than V1. How can V2 be greater than V1? If my V1 is less than V2, there is enough. So I want V2 to pull down to ground for a short duration. So I connected a switch and I closed the switch. If V1 is pulled down to ground for a short duration, then the output flips from plus VSAT to minus VSAT, and then the diode is off. When the diode is off, now it is become a perfect astable circuit. What the astable circuit was doing, the same thing it will do. Now it is going to charge towards minus VSAT, but when it encounters a voltage less than minus VSAT by 2, because this is minus 5, when this voltage touches minus 5.1, when this is minus 5, the difference VD will again become positive. Your output will flip from plus VSAT to minus VSAT. So what is the duration of that pulse? It is 0.69 RC. It is going to be 0.69 RC, right? Okay, so these are the 3 circuits, and questions in GATE exam are only in astable. In monostable, there is nothing to ask, right? If you give a trigger, it is going to change. But all the waveforms we have drawn in the astable circuit, right? Astable is important for competitive exams. Okay, so I repeat 3 ways of 3 modes of operation of an op-amp. One is open loop, 2 is negative feedback. In negative feedback, linear applications we have done. For non-linear applications, we have introduced diode, and we have done a rectifier, clipper, peak detector, clamper, and then we improved them using an op-amp, right? Because the passive circuits have a lot of limitations. We have overcome them using an op-amp. And the positive feedback circuits, I told you, you can have 3 ways based on the output state, right? So you can have a bistable circuit or a Schmitt trigger, you can have monostable, and you can have a clock generator or a relaxation oscillator. So all these circuits we have done, right? Positive feedback, open loop, and negative feedback. Negative feedback, both linear and non-linear. So now, before I go to BJT, a simple motivation for BJT is how a BJT circuit can be used for amplification when it is a non-linear device. When it is a non-linear, for that we have to introduce a topic, the last topic in diode, called the small signal analysis of a diode. It's called what? The small signal analysis of a diode. So once we study this small signal analysis, then we can cruise very easily to go to BJT circuits, right? Okay, so we'll take a break. When we come back, we will see small signal analysis of a diode, right? Take a break. Okay, can you hear me now? Can you hear me? Yeah. So small signal analysis of diode. Small signal analysis of diode. Okay. So what is this small signal analysis of diode? Before that, we all know that a diode is nonlinear, BJT is nonlinear, and a MOSFET is also nonlinear. So all these are nonlinear devices, especially the BJT and MOSFET. But how is that this nonlinear device can be used to build a linear amplifier? Device is nonlinear, but it has to give linear operation, is it not? So if you look at diode, VD and ID, the characteristics is nonlinear. And we know that ID equal to IS into e power VD by VT. All right. Similarly, if you look at other devices like the BJT, what are the three terminals of a BJT? Base, emitter, collector, right? So here you have VB and this is IC. And if you look at the characteristics between VB and IC, it is also nonlinear. IC equal to IS into e power VB by VT. Or if you look at MOSFET for that matter, MOSFET, what are the three terminals of MOS? You have a gate, source, and drain. Am I right? So this VGS, you have ID here. So even if you look at MOSFET, the characteristics is going to be nonlinear between VGS and ID. So how is that when you have a linear, nonlinear device, you can have a linear amplifier like V naught equal to K V in, I naught equal to K I in, V naught equal to K I in, I naught equal to K V in. How can you build a transconductance, transresistance, voltage amplifier, current amplifier, which obeys an equation y equal to mx? Your V naught is K times of V in, y equal to mx. How is that it is possible that with these nonlinear devices, you can build some linear amplifiers, right? So MOSFET is basically a square law device and got some constant K. K is some mu Cox W by L. So doesn't matter right now, okay? So right now, look at the equations. One is the exponential, the other one is a square law device. So with the help of these devices, how we can build a linear amplifier? See, what do you mean by linear amplification? Suppose if the characteristics of BJT, is not nonlinear, it is like a straight line. Suppose if this is the BJT characteristic, then what will happen for this device? This is a linear device, right? Linear device. For this linear device, I applied some voltage, some signal. So some signal. What will be the nature of current? What will be the nature of current? Suppose I'm applying some signal here. Say this signal is like this. Now, what will be the nature of current? So you can take a scale here and you can locate the corresponding point. So when a sine wave moves from here, you can take every point here on the line and you can choose. And then if you try to trace them, you realize that when this sine wave goes from 0 to this peak value, the current will also go from 0 to this value. And then when this sine wave goes here, and you have the value here. So it is understood that when I give a sine wave, I'm going to get a sine wave as the current. And of course, if this current flows through a resistor, it also develops into some voltage. So you can get a linear relationship between V and I. Okay, forget about gain. I'm just talking about the shape of the waveform. At least if I give sine, I'm getting sine. When this test is passed, what if for the amplifier, if I say hello, when I say hello over the microphone, it is expected that I get only hello at the output, right? So if I apply some signal like this, then I'm going to get the same linear output, right? With no change in that, because the characteristics is a straight line. This is a linear device. Now, what happens if I take a non-linear device? If I take a non-linear device and draw the characteristics. I'm having a non-linear device like the BJT or a diode, whatever. And for this device, I'm giving a sine wave. What will happen? If I give a sine wave, again, there is always a corresponding point here. So when I try to plot them here, when I give a positive waveform from here to here, I'm going to get something like this here. If I give this waveform, it's again coming back to 0. In the negative cycle, what happens? In the negative cycle, it's gone. My voltage is getting negative, but my current is 0. So it's almost going to be 0. And then for positive, little signal. So finally, what is my shape of the input? My shape of the input is a sine wave, but my shape of the output is some nonsense like this. With such a device, how we can build an amplifier? Is it not distorted output? Because what is distortion? What is distortion? If the shape of the response and the shape of the input are not same, right? If the shape of the output and the shape of input are not same, then we say distortion has occurred, right? So definitely a BJT if you use or a MOSFET if you use for amplification, you are going to get some useless output, highly distorted output you will get. Are you getting? So it is not fit inherently. BJT and MOSFET is not fit for amplification. Is not fit for amplification. Something has to be done for amplification. Are you getting? Something has to be done for amplification. It's not BJT and MOSFET. So many devices we have, they're all nonlinear only. They're all nonlinear. You take any device, you can take an LED. What is an LED? A light emitting diode. Even an LED for that matter is a nonlinear device. So it also gives distortion, right? It also gives distortion. So what if now what if you build a simple transmitter, right? A simple transmitter where you want to transmit the signal over light. Suppose you apply some signal here, a music signal. This signal, if you allow it to flow through a diode, right? The diode is on, an LED is going to give you some light. This light, you can catch it on a photoresistor. And then the photoresistor output is weak. You might need an amplifier. And then if you connect it to a speaker. Now, I want to build a simple transmitter where I give some, if I give a sine wave here, I have to get the same sine wave output here. Or if I play music here, I have to get the same music. So when will this happen? When will this happen? It happens only when, if I give a sine wave, the current should be a sine wave, the voltage should be a sine wave, the light should dance to the tune of the music. The light should be in sine wave form. And the light which falls on a photoresistor should be a sine wave. The amplifier should get a sine wave and the speaker should get a sine. But how do we know the same sine wave is there? Provided these characteristics of the device are not nonlinear if they are linear. Forget about sine, cos, whatever you give, the same will come. Provided the characteristics is going to be a straight line. If you don't have a characteristics of straight line, then forget it. The device is nonlinear. So this is nonlinear. So the output will be distorted. Output is distorted. Right? So you don't get any output, some nonsense you're going to get. You're not going to get the sine wave here, right? Proper sine wave. Now, how I can convert a nonlinear device into linear, right? So how to convert a nonlinear function, right? A nonlinear device to behave as linear. How to convert a nonlinear device to behave as linear? Very simple. When you have a characteristics like this, now for this characteristic, I told you if the slope is high, you get a large output, right? But you have to choose only this portion of the characteristic, only this portion. And you have to convert the device characteristics to be like this. That's all. Now, if you say that my device is only this, yes, your device. So how does it look like? When you look here, it looks like e power x, right? But what happens if my x is small? My x is small, this is nonlinear, But if my x is small, it is going to convert to 1 plus x. 1 plus x looks to be linear. 1 plus x looks to be linear, right? But how can you choose only a small portion of the characteristic? The moment you switch on, you have to operate only here, right? But how is it possible, right? So how can I apply this sine wave here? I want to apply this sine wave here. Can I apply here? So suppose I have, if I use the whole characteristics, then I'm using till here. I don't want this. I have to use only this. For this portion, I have to do two things. One, I have to choose an operating point here. I have to choose an operating point by first giving some DC voltage, right? I have to bias him at this operating point. So I have to give DC. So you might say, sir, what is the signal? The signal is 1 millivolt, right? Don't worry. You give a DC of 700 millivolt. Big signal you give, big DC, right? Not 1 millivolt signal. 700 millivolt of DC you give. So first, if you give that, the device that is sleeping is just going to get on. And BJT is going to move from cutoff region to active region the moment you supply this 700 millivolt or 0.7 volts. So if you give such a large voltage of 0.7 volts and switch on the device, you are at this operating point. And the next thing is, if you give a big signal here, again, it's the same problem. Here, you have to apply a small signal. You have to apply what signal? A small signal. Then you will choose only this portion of the characteristic, and then you can get amplification. So if you want amplification, then what you have to do? You have to first add some amount, how to convert nonlinear device to behave as linear, right? 2 steps. What are the 2 steps? One, add DC. Adding DC is technically called biasing. Bias the amplifier at an operating point where you have to bias him in the active region at an operating point where the slope is high. The slope is high in the active region, so you add DC. Now, second procedure is keep the signal input sufficiently small. Sufficiently small. When I use the word sufficiently, what do you mean by that? E power x. So where is my e power x in this equation? Okay, where is my e power x? My e power x is here. Can you see here e power x? Can you see e power x here? When x will be small, tell me. Your VB is nothing but Vn, and Vt is 25 millivolt. So the input that you apply here should be much less than Vt. Keep the signal sufficiently small. That means your input Vin should be much less than Vt, or your VBE should be much less than Vt. The input that you're applying, if it is much less than Vt, and you add DC, then a nonlinear device behaves as what? Behaves as linear. So whatever the characteristics of a linear device is there, the nonlinear device also will behave in the same fashion. The reason is inherently the device is nonlinear. So if somebody asks you draw the characteristics of BJT in an EDC class, in EDC class you have to draw like this. Are you getting? In analog class, somebody says draw BJT. What do you have to do? Draw the BJT characteristics of an amplifier. Means like this you should draw. Because we are not going to choose the whole characteristic, we are going to choose only a small portion, because that is where your signal will operate, and there's the dynamics of the circuit is only at this operating point. See here, your voltage, the voltage input is going to fluctuate here. This is a fluctuation, and according to that fluctuation, there's a current fluctuation that's going on there, right? So that's the signal dynamics. So you're not applying a big signal, you're applying a small signal at a small portion of the characteristic, and your voltage and currents are going to fluctuate only within that point. So what's the characteristics of the device finally? The characteristics of the device is almost going to behave like what line? A straight line. So I don't know if it's linear, but I can definitely tell you that distortion will not be there at the output. The distortion is tremendously reduced. Distortion is tremendously reduced, right? So this is the only way. See, I cannot use a resistor for amplification because resistors are what? They are attenuators. I have to use a transistor for amplification, but a transistor should behave like a resistor characteristic. So how is it possible? It is only possible if you don't use the whole portion of the characteristic, if you use only a small portion. So if we don't want e power x, we want 1 plus x. We want to choose only a small portion of the characteristic. As long as your signal fluctuates, your voltage and current is going to fluctuate, right, within a small portion, then the currents at the output are also going to fluctuate, right? When you see the current variation and the voltage variation, if you give a sine wave, you're going to get a proper sine wave here, right? So this way we can avoid what? Distortion. I think so students, you would have done this in the lab, is it not? So what is the experiment you would have done in the lab? What is the experiment you have done in the lab? Tell me. In the lab, first you will give a large signal. Large signal. You add some DC, give a large signal. Then suppose you are playing music, full distortion will be there, right? Output will come, but it will be distorted. Then what you will do? The amplification, you have to decrease it. Slowly you have to decrease. As you slowly decrease it, what will happen? Suddenly the distortion is gone. Then how will you explain this phenomena graphically? Tell me. So you have to explain to your friend. Can you tell him that by one device, first you give full volume, right? Full signal, distortion will come. If you give small signal, nice output you'll get. How will you explain him? How will you explain? As an engineer, how are you going to explain a layman about this experiment, right? If you give a full signal, big signal, a large signal, full distorted, like you're closing your ear, you feel like, oh, this you can play a nice raga, right? You can play an A.R. Rahman song, right? An A.R. Rahman song, if the signal is large at the input, like he's like, oh, this is not the song I want to hear, right? And then you give a small signal at the input, and this is a pleasing song. Now you are an engineer. How are you going to explain this to a layman, a guy who does not know electronics, right? At least he knows what is Y equal to mx. You have to explain him only by looking at its character, right? So you have to tell him that if I give some voltage, this is the current change, and the current changes are applied to the speaker, right? So when I give a sine wave, if I get only the sine wave, if I give a sine wave, I'm going to get only the sine wave, then the characteristics are called, see here, then the characteristics are called linear. There's no distortion. If I give sine, I'm getting sine. If I play music, I'm going to get the same music. If I give a triangular, I'm going to get a triangular. But can I get a triangular waveform as an input if I give for a characteristics like this, nonlinear? If you give some rhombus, some nonsense, you will get. So that means distortion is eliminated only by applying what signals? Small signals. You apply small signal, then the device is now going to behave linear. And the good news is, here, because now the device is linear, see here, what is the change you have to build in the transmitter? Take the same transmitter, show this to your friend, right? Show him, if you play music, you get the signal is distorted. Now you add some DC, around 0.7 volt, 700 millivolt, and you apply a small signal here, small music signal. Here there is a large signal. There's a large signal. When you apply a large signal, what is happening here? Output is distorted. But if you apply a small signal, now what will happen? This DC you're operating here, and when you apply the signal that the LED is going to give is going to have exactly the same shape of the input. And that LED light you're catching on a photoresistor, when you give this to an amplifier, you'll realize how pure this waveform is, right? How pure this waveform. So that means you're using only a small portion of the characteristics of the device. Are you getting? Otherwise, you cannot simply tell him, decrease the signal, nice output will get. If you give large signal, output will not come. So it's some way you have to explain it, right? So the best way is to take the device characteristics. The device characteristics is the slope. Apply your X here as the input, and this is your, say, your output or the current here. Then if you can show that there is a linear variation, then you can convince him that if I give small, I'm going to get the same shape. But if I give large, what will happen if I give large? See, I'm giving large to the nonlinear device. Some nonsense I'm getting here. So that means this device is useless if you give what signals? Large signal. You should always give what signal? Small signal. And this experiment, if you do it in the lab, you will get a pure output, pure output. You'll really enjoy the music. Are you getting? Right? So this way, so finally, 2 steps. I want to convert a e power x to 1 plus x. I want to convert a nonlinear device into linear. What should I do? I should not use the whole characteristic. Don't give, see, if you give a big signal, what is the problem? Complete all regions you will use here. You'll use cutoff region, active, saturation. Who wants, right? Do you want a transistor to work in every region? Suppose this is your transistor characteristics. This is cutoff. This is saturation. This is active, suppose. What happens if you give a big signal like this, a big signal like this? What will happen? This portion, at this portion, it is going to get clipped, saturated. At this portion, you will get some linear waveform. That too, it is not like that. It will be like this. Here there is cutoff. It's all nonsense, isn't that? BJT should be operated only in active region. Only in what region? Active region. No cutoff, no saturation. Are you getting? And that too, active region, this is not a pure straight line. It is going to be nonlinear. So you have to apply a small signal. You have to apply a small signal. Keep the signal sufficiently small. And then you can enjoy the quality of music. Are you getting? Right? So how are we going to convert nonlinear device to linear? Biasing is very, very important. This is why biasing is so important. You have to first add some DC. And then the second step, you have to keep the signal sufficiently small. Now this device, I can call it linear. I can call it what? Linear. But this device is what? Non-linear. And one more good news is, because it is linear, you can apply superposition theorem. What else do you need? What is superposition theorem to a LED or a diode? First to do DC analysis separately, then do AC analysis separately. And what is the total voltage across a diode? It is the summation of DC component plus AC component. The same discipline you will carry on in BJT. When at the moment BJT amplifier is given, VCC supply is there, Vin is there. Nicely apply superposition theorem. Now somebody will come and ask, sir, how you are applying superposition theorem? BJT is having all curves. He said, no, I am giving only this much signal. When my signal is fluctuating, when I say hello, my signal is fluctuating, how much portion of the characteristic it is using? Only this much portion. If you draw that small portion line, that looks like straight line. No? So you can apply superposition theorem for a transistor. So you do DC analysis separately, do AC analysis separately. What is the total voltage or current? What is the base current in a BJT? IB total is IB DC plus IB AC. What is VC in a BJT? VC total is VC DC plus VC AC. VC DC from DC analysis, VC AC from AC analysis. So any voltage and current in devices are split into two components now. What are the two components? A DC component or a static component, and there is an AC component or a dynamic component. Are you getting? So now, what is the discipline we have to introduce here? What is the discipline we have to introduce? This is a diode. For this diode, we are giving DC and AC. Is DC a small signal or large signal? This is very large, 700 millivolt. That means 0.7. 700 millivolt means 0.7. Because this 0.7 is a very big voltage, very big. It's only 0.7, but it is very big in electronics. We will use capital letters for DC. See, if somebody writes VD, that's VD on, it's 0.7. If somebody writes a small v, small d, what do you mean by small v, small d? This is DC component, static component. This is the signal that you are applying here, small signal that you are applying here. It is AC component. So what is the total voltage here? VD. It is a summation of DC component plus AC component. Then how do you write the summation? Summation has DC and AC. So summation should be written with one capital letter and one small letter. See how nicely they have made. This is a universally accepted notation. If somebody writes one big letter and one small letter, it is a total instantaneous value. If somebody writes only big letters, it is DC component. If somebody writes only small letters, it is AC component. It is dynamics. This is statics. What is current here? DC current is capital I, capital D. AC means small I, small d. If I write one capital and one small, it is the total instantaneous value. So please, we have to follow this notation. Are you getting? So we are going to draw, we are going to find the small signal model of diode. So we are going to find the small signal model for the diode. See, that is why the treatment in analog is so different from what you study in BJT. What you study in EDC. In EDC, you might study PN junction, barrier, this, that, everything. But finally, when you come to analog, they say, what are you applying for this? Right? I'm applying DC. Then you neglect the microampere region, treat him as piecewise linear. You can have some linear model like a 0.7 volts or short circuit and then solve. With that, you will do clipper, clamper, peak detector, voltage multiplier and all. Then if you're applying a small signal, that means you're using only a small portion. For that, some model we are going to derive. That model, if you replace the diode with that value, some resistor we are going to replace now. And that's it. We can do DC analysis and AC analysis. So similarly, in a BJT, we are going to know BJT inside might be P material, N material, this, that, barrier and all that. But at the terminal behavior, how it is behaving. If you know, then it's easy for you to analyze the combination. 5 transistor, 10 transistor, if you combine them, it's very, very easy to analyze them, right? You should know its terminal behavior mostly, right? Okay. So tell me, what is the equation for a diode? ID equal to Is into e power Vd by Vt. Eta is what? When I write a capital and a small, it is what value? The total instantaneous value. This is total. It's total instantaneous value. So what do you mean by total instantaneous value? Or if I write only capital letters, then it stands for what? DC. Then I have to write Is into e power Vd by Vt. This is only DC component. All right. Or from here, what is ID? Capital ID plus small ID is Is into e power capital Vd plus small Vd by Vt. Capital Vd plus small Vd by Vt. So this is equal to Is into e power capital Vd by Vt into e power small Vd by Vt. Into e power small Vd by Vt. What is this from equation 1? What is this from equation 1? It is capital ID plus small ID equal to equation 1 says that it is capital ID into e power Vd by Vt. Now all of you, I told you e power x. What happens if x is small? If x is small, it has to be 1 plus x. So e power Vd by Vt is nothing but 1 plus Vd by Vt. Am I right? So it is Id into 1 plus Vd by Vt. So thank God, nonlinear function is gone. Are you getting? So what can I write here? It is Id plus Id into small Vd by Vt is Id plus I. Now tell me, can I cancel this ID? Yes or no? Now defining the diode dynamic resistance. The diode dynamic resistance RD. What is diode dynamic resistance? It is small Vd by small id. Small Vd by small id. It is Vt by capital ID. So a diode is now going to behave like what? A resistor, is it not? So this is the characteristic. And now we are going to use only a small portion of this characteristic. Here we are going to apply the signal here. If you apply the signal, you are going to get a linear output. So let me take a snapshot of this. And here, this one. This is Vd, small Vd. This is small id. Now you understand why did I take a bulb in my first class? Why did I take a bulb in my first class, Ohm's law? It is not for time pass. Why? Because I am going, if you think that you are able to you are comfortable with resistors, that means you should be comfortable with diodes also. Because now I'm going to convert diode into a resistor. A diode is going to behave like a resistor now. Diode, what is a diode for DC? DC, it is going to give you how many volts? 0.7. What is a diode for AC? AC resistance. It is behaving like a resistor RD. RD. What is the value of RD? This value of RD is VT by capital I. It is VT by capital I. So a diode is now going to behave like a bulb. Bulb is what's a linear element. The diode is also going to behave like a small, bulb or a resistor, provided you don't apply a big signal. If you apply a big signal, then you will use the whole characteristic. We don't want. We want to use only a small portion of the characteristic. That means you apply the signal only there. Are you getting? You apply the signal only there. Right? Don't apply the signal for the whole input. For the whole input. Are you getting? Right. So I don't know. See, what is the analogy for this? What is the analogy? See, in olden days, we used to have, fathers are very strict, right? Olden days, fathers are very strict. And when the moment they come home, right? The moment they shout, suppose imagine they are shouting for the whole day, right? So whole day, from morning till evening, like they are after you, then it's like the dynamics is for the whole duration. What if they shout only for a small duration, right? That they control you only for a small duration. If the duration is quite small, then the response is also, once the father leaves the house, again, what we will do? Naturally, we'll take bat, ball, cricket, right? We'll go and play. Are you getting? Because they are there only for a small rinky-dinky portion of the total day, right? But then it's perfect, right? Only for that duration we will study. And after that, rest else is that we are not at all at home. Are you getting? We are somewhere roaming, right? So the device is an amplifier only for this duration of the signal. Rest else, you are not using that. You are not at all using that. It's only for that small portion you are applying it. But the device still has all the cutoff is there, active, saturation, everything is there. But only for that duration you will apply and you will get an output only because of that. Are you getting? Right? So that's a good thing. But when you do this in the lab, what you will do, sir, in the lab, you will give a small voltage to a large voltage. You will give a small voltage to a large voltage, and then you will calculate the whole characteristic. We don't want that. Take a signal of say 3 volt, and then you increase that signal from 3 volt to 3.1 millivolt, 3.2 millivolt, 3.3 millivolt, and only draw that characteristic, because my microphone is going to give me very, very small 1 millivolt signal. So if you draw the characteristic only from 3 volt to 3.5 millivolt, and if you draw, you will realize that it is having a straight line characteristic. So if you apply a signal there at that duration, you add some 3 volt and connect a microphone there, and if you say hello, then automatically the output is always going to be what? Linear. Is it not? So okay, whatever it is, don't forget this. What is the final summary here? The small signal model. What is the small signal model of a diode? Finally, right? The small signal model says that a diode is replaced with a resistor RD, whose value equal to VT by capital ID. What is VT, sir? 25 millivolt. What is ID? What is ID? What is ID? What is ID? ID is the DC current here. The ID is a DC current. So see the beauty here. The AC resistance, which is a slope, is going to depend on the DC operating point. That is why biasing is important. The slope is dependent on the point in the middle, right? The slope is dependent on the point. So who decides the slope is the operating point here. Are you getting? So this is the AC resistance. What about DC? For DC, the diode is replaced with how many volts? 0.7. So this is a DC model of a diode. This is the AC model of a diode, or the small signal model, or the small signal. This is the final summary. Never forget that a diode is going to behave like a resistor. Slowly you will realize transistor also will behave like a resistor. Are you getting? MOSFET will behave like resistor, because you will apply small signal only, right? And you will have a small signal model for the BJT and of course the diode, right? Okay. And please next time don't do all this, huh? Every book will do this, but I'm telling you what is slope, sir? What is slope in mathematics? In mathematics, slope means differentiation. Am I right? So why did I do all this? Because I'm using a notation here: capital letters for DC, small letter for AC, one capital and one small for total. So because we are introducing, I've done this. But for BJT and MOSFET, let us not do all this. Tell me what is slope, sir? Directly, slope. Slope means differentiation. No? ID equal to IS into e power VD by VT. So what is DID by DVD? Differentiation. It is IS into e power VD by VT into 1 by VT. All right. Now tell me, if this whole thing is 700 millivolt and then you add a 1 millivolt signal here, what is 700 millivolt plus 1 millivolt? What is 700 millivolt plus 1 millivolt? Is approximately 700. So IS into e power, capital and small is nothing but almost capital here into 1 by VT. So this is equal to, what's that? What is this? Capital ID by VT. So DID by DVD is nothing but capital ID by VT. What is slope M? This is the slope. So what is resistance RD? RD is equal to 1 by slope, which is change in VD by change in ID, which is nothing but VT by capital I. See, same thing we got, but we did just mathematics, differentiation, because slope is nothing but what? Differentiation. And then we have approximated that value. What is this capital VD? Capital V, small d. It's approximately DC value. 700 millivolt plus 1 millivolt is 700. So at that operating point, your RD is VT by capital I. Now, almost 2 pages we have done here. Are you getting right? It's good because first time we are introducing this notation. But next time we'll not do all this. We will just simply say differentiate, you'll get that value. Are you getting? So this is also one way of solving. Okay. Forget everything. Don't forget this. This is very, very important. This is very, very important. RD is VT by capital IT. So now we are not going to use the complete portion, only a small portion of the gas, only for a short portion, right? When the signal fluctuates like this, the current also will fluctuate by the same amount. Are you getting? But if your characteristics is nonlinear, if it fluctuates from this point to this point, then the output also will have some nonsense because of the curve. Are you getting? So when there is a curve, if you apply a signal, you get some nonsense, right? So if you want y equal to mx, this is the idea. Okay. Fine. So this is a gate problem. Find ID if eta is 1, Vt is 25 millivolt, and Vd on is 0.7. Find the total instantaneous current ID if eta is 1, Vt is 25 millivolt, and Vd on is 0.7. Calculate. Now we are going to split the analysis into two parts, DC analysis and AC analysis, right? Okay. So what is this theorem called? This is called superposition theorem, right? Superposition. So what is superposition? You have to take only one source at a time, right? So the diode which is nonlinear will allow you to apply superposition because the characteristics is almost like what line? Straight line. So first do DC analysis. When you are doing DC analysis, what should I do to AC sources? AC source, right? AC sources are shorted, right? So the AC source is short, we have to apply only DC. And what is the DC model of a diode? The DC model of a diode is 0.7 volts. The DC model of a diode is, the diode is replaced with 0.7 volts. Can you see the DC model, right? DC, this is DC, and this is AC model, AC. Are you getting? DC model. Now what is capital I, capital D? What is capital I, capital D? You can apply superposition. So ID equal to 5 minus 0.7 plus 0.7 plus 0.7, 2.1 by 1K. It is 2.9 milliampere. It is 2.9 milliampere. From here, what is RD? RD equal to Vt by capital ID. It is 25 millivolt by 2.9 milliamp. 25, what is 25 by 2.9? How much value will get? 25 by 2.9. Calculators, 25 by 2.9. What is 25 by 2.9? 8.62 ohms. 8.62 ohms. 8.62 ohms is your RD, right? Now, after doing DC analysis, Now we have to go for AC analysis. In AC analysis, you have to consider only the AC signal, 2 sine omega t millivolt, and the DC short. Each diode is replaced with a resistor. Eight point six two ohms. Now, what is the small ID here? Small ID. Small ID equal to 2 sine omega t millivolt by, so these are all in series, right? 1K plus 3 times of 8.62. So it's almost 1.9 sine omega t milli, is it not? It's almost 1.9 sine omega t milli by kilo, microamp. Very, very small, is it not? Now tell me, what is the total ID now? Total ID is DC component plus AC component. It is DC component plus AC component. What is DC component? It is going to be 2.9 milliampere, 2.9 milli plus 1.9 sine omega t micro. So you can imagine how small is this. See, at least the good thing is diode is not an amplifier. We are just doing analysis, not an amplifier. At least be happy that my input is sine. What is my input? Nature of my input is a sine. When I give sine, I am not getting some triangular output here. What am I getting now? When I apply sine, I am getting sine output only. That means the shape of input voltage and the shape of the current that is flowing in the circuit, both are same. But what did we apply here? We applied a non-linear diodes. See, when you will apply sine, you get sine in networks class. When if I apply sine, I have to get only the proper sine. Means what? Only resistors should be there in that network. But are there resistors in here? No, diode. Now the diode is behaving like a resistor only for that small 2 sine omega t input. You're using only that small portion, right? So the device is now behaving as linear. It's now behaving as linear. So now a diode is not able to give amplification, is it not? If you give a millivolt signal, you are getting microamp of current. Is it amplification? No, is it not? Who will give you amplification? BJT will give you amplification, not a diode. Find V naught by V. Okay. So how do we solve? Superposition theorem. First we have to do DC analysis. Now tell me, for DC, what is capacitor for DC? Capacitor for DC is going to behave like open circuit. DC or low frequency, right? If the frequency is zero, what is 1 by F is 0? 1 by omega C. Omega is 2 pi F. 2 pi F. If F is 0, it is infinite. So what do you mean by infinite ohms? The capacitor is going to behave like an open circuit, right? So we will have a current source here, 1 milliampere, diode, capacitor is behaving open circuit. Now, in DC analysis, what is our aim? Our aim in DC analysis is to get this capital ID. Now here, radially ID current source is already there. What is capital ID? Capital ID is going to be 1 milliampere. So this completes our DC analysis. Our main aim in DC analysis is to calculate the DC current. The DC current is already given by examiner. So ID is directly 1 milliamp. Then what is RD? It is VT by capital ID. 25 millivolt by 1 milliampere. It is going to be 25 ohms. So remember, all the AC parameters you will not get from AC analysis. The AC parameters you will get from DC analysis. So who is controlling whom? The AC analysis is going to be completely controlled by biasing. Is going to be controlled by DC analysis. So DC decides AC. The operating point is going to decide the DC point. The DC currents and the DC voltages are going to decide the AC dynamic resistance, RD. RD is VT by capital ID. This is the AC resistance, but we didn't do AC analysis. We have done DC analysis. So DC is going to decide AC. DC decides AC. What about AC analysis? For AC analysis, capacitors are replaced with short circuit. Capacitors are replaced with short circuit. DC sources, VDC, DC sources are replaced with short circuit. Current sources, DC current sources are replaced with open circuit. So only a diode is there. Capacitor is replaced by short. And now you apply a small signal. Five ohms. And what is a diode AC resistance? 25 ohms. The diode is replaced by 25 ohms. So what is 25 parallel 25? It is 12.5. So now you can apply voltage division. V0 is going to be how much? This is 12.5. It is 12.5 by 12.5 plus 5. Plus 5. This is V0 by V. So you can apply voltage division. Are you getting? So you have 5 ohms here. You have 12.5 here. 3. So it is 12.5 R2 by R1 plus R2. Is it not? Suppose this is R1, this is R2. So this is going to be V0 by Vn is going to be R2 by R1 plus R2. All right. So this is the answer. So what is 12.5 by 12.5 plus 5? It is 12.5 by 17.5. How much is 12.5 by 17.5? 0.714. So what is capacitor for AC analysis? If the frequency of omega is larger, the mid-frequency range, the impedance offered by capacitor XC or 1 by omega C, if omega is large, is approximately 0. So for high frequency, for even the mid-frequency, the capacitor is going to offer low impedance. So AC analysis, capacitor should be short. DC analysis, capacitor should be open. Your answer is 0.714. Take down, find V naught by V. Find V naught by V. Okay. So how to solve this? First, we have to do DC analysis, superposition theorem. For DC analysis, you have to replace voltage sources with short circuit, capacitors with open circuit for DC, but there are no capacitors here, no problem, right? So each diode is replaced by how many volts? 0.7. This is 100 ohms. All of you, if I ground this terminal, what is the voltage here? 0. Here there is a drop of 0.7. If I go up, it will be 0.7. What is 0.7 minus 0.7? This is 0. Right? So this is 0. This is minus 0.7. So I'm having 1 milliampere. What is the current through each diode? What is the current through each diode? This 1 milli. This current and this current should be 0.5 milli and this 0.5 milli. Because this is 0, this is 0. Here the current is 0. And of course, this is 0.5 milli. This 0.5 milli. So Kirchhoff's law is satisfied, no? The 1 milli is simply split into 0.5 milli and 0.5 milli. That's all, 0.5 milli. So each diode has a current. Suppose you treat this as D1, D2, D3, D4. So what is ID1 and ID2? ID1 equal to ID2 equal to ID3 equal to ID4 equal to ID. That's all, right? What is ID? 0.5 milliampere. So what is RD? It is VT by capital ID. It is 25 millivolt by 0.5 milliamp. It is around 50 ohms. It is around how much? 50 ohms. Each diode is replaced by 50 ohms resistor for what analysis? AC analysis. So for AC analysis, DC sources are replaced with short circuit. Current sources are replaced with open circuit. So now each diode is replaced by a resistor. (50 ohms). And here you have 100 ohms. And this is V. All right. So please replace current sources by what circuit? Open circuit. All right. So what is 50 in series with 50? 100. 100 parallel 100 is 100 parallel 100 is again 50 ohms. This is 100 ohms. So what is V naught by V? It is 100 by 100 plus 50. It is 100 by 150. 52 is 100, 53 is 100, 2 by 3. So the answer is 2 by 3. Now, because this is 0 and this node is 0, what is the current through 100 ohms? 0 minus 0 by 100. So the current to 100 ohms is 0, right? So the 0.5 milli, 0.5 milli is clearly split. 0.5 milli, 0.5 milli, 0.5 milli, 0.5 milli. Overall current is 1 milli, right? Now, this problem is something related to our first class. First class, I told you, the output is always limited by the supply limits. Are you getting? If suppose the op amp output is between plus 12 and minus 12, where will you choose the operating point DC? That is almost 0. So that you will get symmetrical swing. Your positive peak should be equal to negative peak only when the DC is at 0 and you have plus 12 and minus 12. Are you getting? Suppose you have 0 and 5 volt, 0 and 5 volt. This is 0, this is 5. Where will you fix the DC? Somewhere at 2.5 volt. So that your positive peak is equal to negative peak. Are you getting? So similarly, the question is, an amplifier has clipped output above, an amplifier has clipped output above 10 volt and below 1.5 volt. It has clipped output above 10 volt and below 1.5. So it will work only between 1.5 and 10. Now the question is, find the DC point for maximum symmetrical swing. That means your positive peak should be equal to negative peak, right? Similarly, if the DC point is chosen at 5 volt, suppose the DC point is chosen at 5 volt, find the undistorted peak. So simple, is it not? So an amplifier has clipped output above 10 and below 1.5. Find the DC point for maximum symmetrical swing. If the DC is chosen at 5 volt, find the undistorted peak, right? Simple question. Orally, you can do it, right? Okay. So the examiner says that he has an amplifier that works only between 1.5 volt and 10 volt. And he wants to choose the DC in the middle so that you get symmetry. Symmetry means this should be VM and this should also be VM, peak. What should be DC, right? So how will you calculate? Your VM is nothing but, this is VM, positive peak, negative peak should be same. VM is nothing but 10 minus VDC. Your VM is nothing but 10 minus VDC, am I right? Your VM is nothing but 10 minus VDC. But I'm having negative cycle also should be VM. So it is VDC minus 1.5 volt. So your 10 minus VDC should be VDC minus 1.5. So what does the mathematics tell you? 2 VDC equal to 10 plus 1.5, or VDC is 10 plus 1.5 by 2. VDC is 10 plus 1.5 by 2. So 11.5, it should be 5.75 volt. So you have to choose the operating point at what voltage? 5.75. You have to choose at 5.75 volt. Are you getting? So let me see if we are correct. What is 5.75 minus 1.5? Is it same as 10 minus 5.75? Yes or no? Your positive peak and your negative peak should be same. Your positive peak and your negative peak should be same. Am I right? 5.75 volt is in the middle point between 10 volt and 5 volt. Is the middle point between 10 volt and 5 volt, right? But please don't take difference and then by 2. Are you getting? You should not do, right? Don't take difference and then do by 2. You will not get the middle point, right? Suppose what is the middle point between 2 and 10? 2 and 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Are you getting? Between 2 and 10, you will have 6. Yes or no? Because 6 minus 2 and 10 minus 6 is same. But if you do 10 minus 2 by 2, 10 minus 2 is 8 by 2, 4. Between 2 and 10, how 4 will be the middle point? Is it not? So don't do that. Your positive peak should be equal to negative peak. 10 minus VDC should be VDC minus 1.5. Are you getting? Simple mathematics, right? Okay. But if you have chosen at 5 volt, then what will happen? Your output cannot go less than 1.5 or above 10. But what happens if you choose at what voltage? 5 volt. If you choose at 5 volt, then what will happen? If you choose at 5 volt. Remember, when somebody asks you to draw a sine wave, you should never draw a sine wave like this. Like this. You should never draw like this. You should not. This is wrong way of drawing sine wave, right? You should never draw. How you will draw? You should draw a sine wave. When you draw a sine wave, the positive peak should be equal to negative peak. Are you getting? Or you should not draw a sine wave like this, right? So you take a big wave like this, and then like this, and then clip. This is also not sine wave. Are you getting? This is also not sine wave. Sine wave, this is right. your positive peak should be Vm, your negative peak should also be Vm. So for undistorted output, you should see who is nearer to 5. Who is nearer to 5? 1.5 volt or 10 volt? Who is nearer to 5? Naturally 1.5 volt. So from here to here, if you go 3.5 down, then you have to go only 3.5 up. Then you will get symmetrical swing. If you go and reach 10, then you will have big positive, small negative. That is not at all a sine wave. So if you want an undistorted sine wave, or if you draw a big 10 volt wave, right, from here to here, and then can you come down to 0 volt? No, right? You should not draw like this also, right? This is wrong. Don't draw. Are you getting? Don't cover the whole thing, right? Because here 5, here only 3.5. So you should choose this smallest, the nearest one. So you will have 3.5 down and 3.5 up. So now what is the peak value? Undistorted. Peak undistorted should be how much? 3.5 volt. And what is peak to peak undistorted waveform? Undistorted is nothing but 3.5 down, 3.5 up, 7 volt. Should be 7 volt. Are you getting, right? Never draw a sine wave. So you should choose from 5. Who is nearer to 5? 1.5 or 10? 1.5. So you come 3.5 down and 3.5 up. Right. So this is waste. Now we cannot do anything. But if you choose this big waveform, then down portion also should be big. But can you go all the way from 5 to 0? No. Because the amplifier, what is the statement here? The amplifier has clipped output below 1.5 volt. It has clipped. Can you see here? Clipped. Don't go below 1.5. Are you getting? When you will go below 1.5, if you choose from 5 to 10, that means you are going below 1.5. Then the signal will naturally get clipped. So what is the answer for this? Peak undistorted is 3.5. Peak to peak undistorted is going to be 7 volt. Are you getting? Okay. Fine. We'll stop for today. Any question and answers? Any doubts you have, you can ask. So any doubts you have, you can ask. Okay. You can ask Venkat. Unmute Venkat.
Sir, sir, okay, sir. Okay.
Yeah, tell me. Yeah, you can ask now.
Hello.
Yes.
So I have a doubt like the diode will always operate in the 0.7 VDC, right?
Yeah, that is only for DC. Yeah.
How it will change, how the operating point will change with the different values of DC current for the same
Operating
diode?
point will change for operating point is always the same. The operating point is nothing but the DC current, no?
Yes, sir. But in a diode we can change the DC current.
Huh?
But in a diode we can change the DC current values, no, sir. So
Yes,
the
you
operating,
change the resistor in series, it will change, 5
So-
volt in series with 1 kilo ohm, 0.7, 4.3. If you put to 2K, you will have 2.25. If you put to 10K, you will have 0.57. So if the series resistance changes, the load changes, automatically current will change, no? See here, I am having 5 volt.
yes,
This is a diode. What happens if this DC resistance changes? Operating current ID will also change, no?
yes, sir.
Ah.
But it has only one curve, no, sir. At
Only one
0.7,
Yes.
it has only one characteristic curve.
Yes,
At
one
0.7, at 0.7 voltage, it will have always one current, one ID.
Yes, that is a static point. So this, suppose if you give only 0.7, then this is the current flowing. Now tell me, this is not small signal analysis, right? What is diode? Diode has some characteristics. On that characteristics, one dot you are using. That's all.
Yes, sir.
What you will do with that dot? Now you have to apply a signal. At this point, if you apply a signal and choose a portion of the characteristic, then in a BJT you might get amplified. Suppose in a BJT you're doing only DC analysis. Means what? Only you're doing this. That's all. One dot you will get somewhere. Some DC current will be there, some DC voltage. With that, no amplification you will get. At that active region, you have to apply one signal, one microphone you have to connect. Then you will get amplification.
So my doubt is like the ID will be same for the diode. It will not change, no, sir.
Yes. ID is fixed. Static current is fixed. Small ID will change. Dynamic current will change when I apply signal.
Okay, sir.
If I apply a signal, then this signal is dynamic. This is dynamic. And this is static. Static will always depend on 5 volt DC. If the DC is fixed, DC current is fixed. If AC changes, the dynamic ID will change. Small ID.
Oh, okay, sir.
Yeah.
Hello, sir.
Yes.
Hello, sir. Sir, 15F.
15F.
Yes, sir.
Yeah.
Sir, here you assume that case one like that VSAT is plus 10 volts. That means if assume VSAT is equal, means if we assume the stable state as negative, then this diode will become reverse bias, sir.
Yes. Diode again it will charge to that value, and again it will come back to plus VSAT, and then again the diode will be on. So if you have a cup of coffee and gum, again it will come to VSAT and stay there.
Sir, like means if we want to it practically, so then means how to place the diode, sir? We should place, because here we are assuming that the V naught is plus 10 or minus 10. We are doing the problem like in practically if we want to do. So if we want to do it in a circuit.
See, if you use the same circuit, Then first day, when you come and operate the device, no?
Yes, sir.
When you come and operate the device, you are saying you don't know whether it is plus VSAT or minus VSAT.
Yes,
After
sir.
that, it will always be at plus VSAT. Okay, first time only you have a problem. So if you use the same circuit for a motor, means first time little coffee will come, some hot water will come, and after that it will come to a stable state, and then from there it is going to operate. What is the problem?
Okay. Okay, sir.
First duration, see, when you switch on, noise is generally positive in nature. When you switch on, dynamically the output will always shoot to plus VSAT. It will not come minus. Even if it comes, the diode will be off, capacitor will charge, no?
Okay,
And
sir.
what will happen when the capacitor will go below that value? Again, it will go to plus VSAT, and then the diode will get on. So before you come and see, it is already there at the same plus VSAT. What do you?
Okay, sir.
Yeah.
Sir, next thing is 29F.
29F.
Just a small doubt, just about the analysis of the circuit in 29F.
Yeah.
Sir, here, here you are taking because this 25 ohms and 25 ohms are in parallel. You are taken 25 ohm by 2, 12.5.
Yeah.
So like means I'm so my doubt is that like here 5 ohm and 25 ohm is there. So here if we take the voltage at this node, the junction of 5 ohm and 25 ohm, then this V0 and that voltage will be, means what are the voltage will calculate, that will be in parallel now, sir. Then voltage will be the same now.
Yeah, voltage will be. So you want, see, if you don't want me to do like this, you can do like this. You are saying this voltage parallel, V0, no?
Ah,
Am I
yes,
right?
sir. Yes, sir. Yes, sir.
Yeah, then you can do entering current equal to leaving current. Same answer you will get. V in minus V0 by 5 equal to V0 by 25 plus V0 by 25. Is it okay?
Yes, sir.
Entering equal leaving. From here, V0 by V in will be 0.714. Same.
Means means I'm telling like here for 5 ohm and 25 ohm will behave like a voltage divider now, sir. So
No. If current is same, then it is a volt. The current is getting divided now. How you will apply voltage division?
Okay.
For voltage division, same current should flow. No?
Hello.
If you combine it to 12.5, then same.
Hello, sir. Hello.
Yeah.
Okay, sir. Thank you very much.
Hello,
Yes.
sir. In page number 15F, sir.
Yeah.
Sir, can you explain about the trigger circuit, sir? Why can't we directly connect it to
If
the
you want,
ground?
you can give directly. That node is, if you short it to ground, then spark might come. No, we generally avoid whenever you are redirecting that path direct to ground. Some device you have to use which will oppose that change. So the chance of getting spark is avoided. Capacitor will put some 100 microfarad capacitor. If you put electrolyte, just when you press, it will oppose that change. That's all. If you want directly, you can give also.
Sir, now how this works, sir, when the switch is closed?
Capacitor is already at zero, no, because of that resistor.
Okay, it's
See,
already.
whatever voltage is there, here it is getting discharged to resistor, no?
Yes, sir.
Capacitor is always at zero only.
Okay.
The moment you close, this point here, V1, is pulled down to ground.
Okay.
It
Sir,
is only to oppose that change. Yeah.
in this way, suppose if it is at initially at minus VSAT, we didn't even close the switch, no, sir.
We didn't even close, yeah. Initially, we thought it is at plus VSAT.
No, sir. Suppose if it is at minus VSAT.
If it is at minus VSAT, then V1 will be minus 5, no?
Okay.
Then diode will be off, no?
Diode, the voltage at the diode will be
Off, because of minus VSAT.
like.
You are giving, see here, this is a resistor R,
Yes, sir. Yes, sir.
capacitor is there, diode is there.
Huh.
Now, if you give plus VSAT or minus VSAT, what is the difference?
Okay.
For plus VSAT, it is on. For minus VSAT, it is off, no?
Yes, sir.
With minus VSAT, the diode will be off. Capacitor will charge. Capacitor will go below minus 5. Again, the output will switch to plus VSAT.
Plus VSAT.
So by the time you come and see, it is again at plus VSAT only.
So here in this initially, if we give minus V set, there is no need
No,
of
no, no.
the
You are
trigger.
not giving. You will only switch it.
Yes, sir. The trigger
If you
setting is not.
when you switch it within a microsecond time, everything will happen, and after that it is at plus V set. Diode is on.
So initially we won't use trigger circuit, no, sir.
No, 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 no. We don't use.
Yes, sir.
That is why in the first diagram I have not drawn trigger.
Yes, sir.
Okay.
Yes, sir. Thank you, sir.
Yeah, yeah.
Sir, in 34F.
Sir, hello, sir.
Sir, 34F.
34F.
So last page.
Yeah.
No, sir, 33. Sir, 33F, sir. Sir, one small doubt only. How can we identify that it is asking us to find the VM? It is asking that we need to find the undistorted peak. So can't it be
Peak
V naught is equals to 8.5?
not very distorted means you should expect symmetrical swing.
Yes, sir.
Symmetry. What do you mean by symmetrical swing? Your positive peak should be equal to negative peak.
Negative peak, yes, sir.
So now you have 10 volt and 1.5.
Yes, sir.
You draw any waveform
Yes, sir.
other than the waveform that I've given, it looks very odd.
Yes, sir.
You try to draw from 0 to 5. Suppose if you draw like this, 0 to 5. See, 1.5. This is 5 volt. Here there is 10 volt. If you draw like this, how will it be? If I suppose draw one big 5 volt waveform and one small 3.5, is it sine wave?
No, sir.
No. Okay. Suppose if you draw one big 5 and another small 5 here, is it okay?
No, sir.
It will be okay, but below 1.5 it is getting clipped now.
Clipped. Yes, sir.
So how will you draw? The only way is you have to reach to the smallest, nearest one.
Yes, sir. Yes, sir. That is what I am getting. But I just want to ask that how can we identify that it is asking us to find the VM? Like for me, I am getting that we need to find
VDC is
V
chosen at
naught.
5. See here, if VDC is chosen at 5,
Yes,
find the undistorted peak he's asking. Correct only, no?
So sir, it can be
Value will only be if you draw symmetrical swing.
it can be the maximum value of V naught also.
Yeah, if you draw maximum, there is no sine wave in this world with a big positive and small negative.
Okay.
That
Okay,
is why I
getting, sir.
told you, never ever in mathematics you should draw sine wave like this. Should never
Okay, sir.
draw.
Okay, sir. Get it, sir. And sir, in 8F. So there are time period problem. I think 10F only.
This one.
Sir, next one, sir. Next. Yes, sir, this one.
Yeah.
Sir, I didn't get the concept that how you identified that tau is equals to RAC.
I substituted there.
Where, sir? 8F, I think. Yes, sir, this one.
Yeah, here. So here you have no answer. Minus RC log R1 by R1 plus 2R2. Why this 2 has come? Because T by 2 is there, no?
Yes, sir.
I am putting T1 here. If I put
Oh.
T1 here, then this T by 2 in the place of T by 2 is T1. Minus RC log R1 by R1 plus 2R2, no?
Yes, sir.
That is what I wrote there. Minus RC log R1 by R1 plus 2R2.
Sir, not getting, sir.
No. This diagram is there, no?
Yes, sir.
You draw the same diagram. This T by 2 is there.
Yes, sir.
Here you write T1.
Okay, sir.
And wherever T by 2 is there in this waveform, only here.
Yes, sir.
E power minus T by 2 RC is there, no?
Yes, sir. Yes, sir.
Here you have to write T1. Then here you will write T1. Here you will write T1. Here you will get T1. Here this 2 will not be there. Because it's T1.
Okay. Yes, sir. Get it.
Yeah, that's all.
Get it now. And sir, in the problem which we just did to find V naught by Vn, there we don't need to check the that the diode is reverse bias or forward bias. It is mandatory that it can be also be forward biased only.
Yeah. In small signal analysis, you are saying.
Yes, sir.
Yeah, generally, when you are applying a signal, the device should always be on, no? Biasing should be there. See, suppose I am designing a common emitter amplifier.
Yes.
Somebody is asked what is the gain. It is understood that the device is on, no? It is not like device is in cutoff.
Yes, sir.
So in every small signal analysis problem, it is the examiner's job to see that the device is on.
Okay, we don't need to check that the diode is on or off.
It will always be on. Anode will be positive.
Okay. Fine, sir. And sir, and one more thing, that the formula which we had just wrote, ID is equals to IS into e raised to power minus t by tau.
Ah,
But before we did one formula in which neta Vt is there. So it is compulsory that in all the problem neta is equals to 1 only.
no, in two gate problems are given. In that,
Yes, sir.
eta is given as 1. That is why in problem I have taken eta 1.
In the problem only it is given. We don't need to identify that.
Given in the problem, no? Eta is 1.
Yes, sir. Yes, sir.
Yeah.
Okay. Fine, sir. Thank you.
Right.
Thank you, sir.
Sir, could you open 33F, sir?
What?
33F.
Yes. 2-3 voices are there. 33F.
Yes, sir.
Yeah.
Sir, in the second part, it is asked means like the undistorted peak. So peak should be 8.5. No, means the gap you have to 3.5. Then it should be 8.5. No, the answer part.
Peak is 8.5.
Sir, it is asked the undistorted peak. So I wanted to know. Means like
8.5.
okay, no, you mentioned peak undistorted equals to 3.5. So I asked means like answer would be 8.5 or 3.5, sir.
See, between the difference if you take, that is peak to peak. Peak means from the middle point you have to take the nearest value so that you get a proper sine wave. The middle value is DC, no? This is DC.
Okay.
This is DC.
Yes, sir. Yes, sir.
Above and below you have to draw the waveform.
Sir, waveform I got means like the answer would be undistorted peak. It is asked then peak.
Waveform like this, sir. Suppose I want you to draw a sine wave between the 2 points. You will draw like this, sir.
No, sir. No, sir.
Then this is what you want, no?
Okay, means like, sir, I just know, sir, the graph which you drew that I got, sir, everything is perfect. I wanted to know means like this undistorted peak is mentioned the swing means like
To
swing
peak is 7. Peak means from the DC above or below. You have to take.
Okay, sir. Okay.
Right.
Okay. Thank you, sir.
Okay. Next.
Sir, can you once please go to 30F, sir? Hello? Sir, can you once please go to 30F page number, sir? Hello?
Tell me.
Sir, can you once please go to 30F page number?
30F.
Yeah, sir.
Yeah.
I didn't take a screenshot.
Tell me.
Okay, sir. I missed the screenshot, sir. Sir, on another doubt, sir, whenever we introduce a trigger for short duration, the voltage at that terminal is 0, sir.
What? Whenever?
We introduce trigger for short duration, then the voltage at that terminal is 0.
At that point it is 0 for that duration. Other end is at 0.7, no? So naturally output will change
Okay, sir.
from
Sir,
plus
one
V.
more doubt is, sir, you said inverting, non-inverting is square wave and inverting is sum. Why it is so, sir?
Non-inverting is?
Square wave, you said something, no, sir? It is square wave.
No, it is a voltage divider, no? If output is square wave, non-inverting will also be square only, no?
Okay, sir.
See here, all of you. See, I am having a voltage divider, R1 and R2. This R1, R2. R1 is 1K, R2 is 1K. Right. Here my V0 is there. If V naught is a 12 volt square wave, what will be my voltage across R2? It will be 6 volts now. Yes or no? Because two resistors are of what value? Same. This voltage V1 is going to be V naught by 2 because of voltage division. So same thing here. If you have 1K here, 1K here, and if your V naught is there with a square wave, then your Vin will also, this V1 will also be Chota square wave here. Are you getting?
Oh, yes, sir. Okay, sir. I got it, sir. Thank you, sir.
Yeah.
Good night.
Hello, sir.
Yes.
Sir, I had a doubt in 26F page.
Yeah.
Sir, here in the DC, I mean, if the voltage, DC voltage is given as +5, if it is sort of reversed, then ID will be, then diodes will be reverse bias and ID will not be there, na, sir? Is it true?
Diode will be reverse bias.
If the 5 volt is reversed, I mean, polarities is reversed in the question.
Yes. Then you are right. With 2 volt sine wave, you cannot get make the diode on. You are right.
Yes, so, and another thing is we are using small signal model and you explained about it. That was very good. And I wanted to ask is how small it is, it should be to consider it as, I mean, small signal model. We approximated e power x as 1 plus x.
It should be less than VT.
It should, okay. The sign, okay. The AC signal should be less than VT. That's is that?
Because it is IS into e power VD by VT.
Yeah, yes, sir. Yes, sir.
Very good.
VD.
Good doubt. Because how small is a small signal? That is very important. If I give 50 millivolt signal and if I say it is small, that is wrong. Right?
Okay.
It should be comparable with VT. It should be much less than VT.
Okay, and sir, another thing, if that we are actually we derived that RD value by using eta equals to 1, I think. So if for some questions eta is equals to 2, then RD will be changed, no sir? Because if we differentiate it, then 1 by eta VT, I think we will get.
You are right, absolutely right. But generally in gate problems, first of all,
Yes,
eta is not there for BJT. When we are doing small signal analysis is generally for BJT. If
Yes,
only 2 problems, I think they are given for diode, and in those 2 problems, eta is 1.
okay.
Sometimes the examiner will not even mention eta. Then also you have to take 1.
1, yeah. Okay.
Yeah.
Okay. Thank you very much. Thank you very much.
Hello, sir.
Yes.
Sir, I have small doubts, sir.
Yeah.
Yes, sir. One circuit is there. If from positive cycle, one diode will be on. From negative cycle, one more diode. Then, if we want to calculate KVL from negative path, do we need to change V in polarities actually?
No. Whether it is positive, if it is positive cycle, substitute positive values. If
But
it is
sir,
substitute
I am going wrong, sir.
Huh?
Can you write, sir? Can you?
Remember, whenever we are giving V in to a capacitor will get polarities because of V in. V in will not get polarities because of capacitor. V in will always be V in. Suppose I want to know the capacitor voltage. The diode is in reverse bias. I might take the polarities reverse and know the capacitor. But capacitor, after finding capacitor voltage, what is V in? V in will have positive cycle, negative cycle. V in will also be 0, no? A sine wave is there. Won't you get 0 for a sine wave?
Yes, sir.
Then what you will take? Once you take positive, once you take negative, what about 0? That is why don't take anything. V in should be V in. Substitute V in as positive values for positive cycle, negative values for negative cycle.
Sir, that I got, but calculation I'm not getting. Sir, can you write one from negative path KVL?
Yeah.
Whatever.
You can send me WhatsApp. No, it's difficult to because
Sir, just a small
tell me.
circuit, sir. Take from negative path. Whatever it is, it's okay, sir.
Okay. Tell me.
One diode or something.
Okay, diode.
Negative path, sir. Reverse.
Like this, you want me to draw?
Yes, sir. Then 6 volts, sir.
6 volts.
Anode.
Connect here.
Anode. No, sir. This is V in. Where you are writing is it is V in. Yes, sir. Then for anode it is 6 volts.
Here it is 6 volts.
Yes, sir. Then in there is a capacitor, sir. Upside.
Here.
There. Sorry to ask a small doubt, sir. Actually, I'm not getting calculation.
What is this?
Okay, sir. Write directly KVL, sir, down.
Yeah, tell me.
Sir, KVL from negative path, I want to know, sir. I'm not getting it.
Suppose your Vn is a sine wave or a square wave of
Yes,
10
sir.
volts.
Yes, sir.
Okay. Now
Yes,
the
sir.
diode is on for what cycle? Negative cycle.
Yes, sir.
This is a capacitor polarity. Am I right?
Yes. Mm.
Yeah. Now you can write KVL. So for what voltage Vn, the diode is on for minus 10 volts. Yes, sir?
Yes, sir.
Diode is on. Now write KVL. Minus to plus. Minus 6 plus Vc plus of minus 10 volt equal to 0. Vc is going to be how much? Minus 16 volt.
Now I understood, sir. Actually, I'm seeing only circuit, sir. That is right.
Yeah, one more thing I will tell you. Capacitor is there, no?
Yes, sir.
Positive plate is already at 6. By the diode, this node should be at minus 10, no?
Yes, sir.
So this is plus, this is minus. What is the potential difference? 6 minus
minus 10. 16.
uh,
Yes, sir. Thank you, sir.
Okay.
Hello, sir. Hello, sir.
Yeah.
8F, sir. 8F.
8F, huh?
Yes, sir.
Tell me.
Sir, in that second step, not understand, sir. Third step. R1, 1 plus R2, there.
This one, huh?
Hello, sir. Yes, sir.
V side you take common, no?
It, left side, sir.
Left side V side, this V side gets cancelled. V side cancel, V side cancel, no?
Okay.
Then you'll get this.
In yesterday's class, sir.
What?
In yesterday's class, 40 minutes.
Yesterday's class, huh?
Yes, sir.
Tell me.
49.
Yeah.
Non-inverting 49, sir.
49F, no?
Previous page 48. 48.
Yeah.
Sir, in this V less than minus R2, V set by R1, how, sir? How is it?
How you will get Vn equal to minus less than minus R2 is that? See, in this equation,
Yes, sir.
can you see equation 1 here?
Yes, sir.
In this equation 1, when V1 will be less than 0. That means your V1 should be less than 0 means how much? 0 minus 0.00000001 like that. Slightly less than 0. So in this equation, you substitute V1 equal to 0. If you substitute V1 equal to 0, what is V in? V in is going to be minus R2 sat by R1.
Okay, sir.
Okay. Or you, instead
Minus
of
also.
V1 is less than 0, you say V1 equal to 0 minus. So what do you mean by V1 equal to slightly less than 0? Substitute 0 and C, then you will know V in equal to R minus R2 V sat by R1. Which means that if V1 should be less than 0, your V in should also be less than minus R2 V sat by R1.
Same at V1 greater than 0 also.
Same case is V1 greater than 0. Here V1 is greater than 0. The same equation I substituted V1 0, you get V1 V in greater than R2 V sat by R1. See, it is better. You see, it is better. You take up 1K, 2K and analyze here. What is there? Suppose instead of saying minus R2 V sat by R1, suppose I am having two resistors, V1. This is V0. Suppose this is 10 volt. This is 1K. This is 1K. How much voltage should be here to make it 0, you tell me? It should be minus 10, no?
Minus 10.
Yeah. What is the current here? 10 minus 0 by 1K. How much current? 10 milli, no?
10
If
milli.
current should flow 10 milli, this voltage should be minus 10, no?
Yes, sir.
Yes or no? Then only same current will flow. What is this minus 10? If this is R1 and this is R2 and this is VSAT, this minus 10 is nothing but minus R2 by R1 times of VSAT. Yes or no?
Yes, sir.
Because R1 and R2 are 1K, 1K. Yes or no?
Yes, sir.
Yeah. Next.
Sir. Hello, sir.
Yes.
Hello, sir. Sir, in yesterday's class, check whether the feedback negative, positive. That problem.
Check whether the feedback is negative or positive. Yeah, tell me.
Sir, when the voltage is short, how VPS becomes 0, sir?
If the voltage is short, this is connected to ground, no? Naturally, this voltage will be 0.
For V minus also, voltage is 0.
No. We are checking. We are not applying virtual ground here. If you apply virtual ground, that means you are saying that it is negative feedback, no?
Sir, same case in negative also.
We have to remove op amp from there. We have to remove op amp and calculate V plus and V minus separately. If you short here, your V plus is at 0 and your V minus, because of voltage division, will be some value. So your V minus is greater than V plus. That is why it is negative feedback.
Okay.
Okay. Yeah. This is 1K. This is 3K. So 1K by 3K plus 1K, 0.25. This is at 0. So 0.35 is greater than 0. Minus is more than plus. Negative feedback.
Hello, sir.
Yes.
Sir, I have a doubt in small signal, sir.
Yeah.
like whatever signals we are making last signal to small signal to make it compute easy, no sir. But in real time, all the signals are large. So do we have to step them?
Our main intention is to see that if you give a large signal, you get a distorted output.
Yes, sir.
But the signals, real-time signals, which are coming from a microphone,
Yes.
the transducers will give very small signals.
Oh,
Basic
okay.
amplification. If your signal is already large and it is amplified, it doesn't need an amplifier. No?
Yes, sir. Yeah, got it.
Amplification means a weak signal should be made strong or large.
Okay, sir. Sir, I have just one common doubt. When AC and DC supplies are given to circuit, how do they interact, sir? I didn't understand that concept.
What is there to interact here? If a plus supply is there, minus supply is there, means somewhere in the middle, when you take the output will have any voltage between plus and minus.
So will those two voltages collide, sir? Like both
Why
AC
collide?
and
They
DC?
have only two voltages, that's all. It's like in a network, you have two supplies. One 5 volt, one 6 volt if you have. Will it collide? They will only satisfy Kirchhoff's law, KVL, KCL.
Okay, sir.
Yes, sir. No. Suppose I am having a 5 volt here. If I give it to minus 5 here, what will happen? 5 minus of minus 5, 10, 1K, 10 milliamp will flow. What is the problem?
My doubt is actually one voltage is AC, sir.
Like this here. This minus 5, this plus 5. If you take the output here, this output will be anywhere between minus 5 and plus 5.
Yes, sir. This I understood. But if this 5 volt was some AC signal, sine T, 5 sine T or 6 sine T.
Here the input you have to give. At the collector you cannot give. This is supply where you get the output. This input.
Sir, in this you use transistors, sir, to combine AC and DC signal. In general, if you don't use transistor, we just connect to AC supply and DC
You don't
supply.
have to worry. If DC is added to AC, the AC will not change its shape. It will only clamp.
Okay.
If 5 plus 2 sine T is there, your sine wave is happy. It is intact. It is just sitting on this 5 volt.
Okay, sir.
A sine wave and a triangular wave are given means then okay. They will interact. AC plus DC, what will happen? Nothing will happen. Your sine wave is still happy.
Okay, sir.
Are you getting?
Yes, sir. Got it. Thank you, sir.
Hello, sir.
Yes.
Sir, while we are doing AC analysis, if you have inductor, even inductor have to do short, sir.
Yeah, for DC analysis, capacitor is an open circuit, inductor is a short circuit.
Okay, okay.
For AC analysis, capacitor is short, inductor is open.
Okay, sir.
Inductor will always give you a complementary picture.
Okay,
Whatever
okay.
you are doing for
Oh.
capacitor, no?
Yes.
Exactly complementary, you have to think about an inductor.
Okay. Sir, it's like what if in the interviewer ask why you're doing open circuit and short circuit?
You are applying superposition theorem. How you want to solve?
Okay.
Capacitors are there in the circuit.
Mm.
Resistors are there. We want to apply Kirchhoff's law. We want to make circuit simple. What you will do?
Oh, okay, okay.
In the
I
mid
thought there reason.
capacitor impedance is very small.
Yeah, okay, sir.
High frequency also capacitor impedance is very small. But low frequency we have to consider.
Yeah, okay.
All this is mid frequency analysis.
Okay, sir.
So if the examiner asks, I'm using a microfarad capacitor,
Yes, sir.
frequency of say 10 kilo radians. Then what
Okay.
is by omega c? Omega is 10k, 10 power 4.
Yes, sir.
Is 1 microfarad. 10 power 4 into 10 power minus 6 means 1 by 100. 1
Yes,
by
sir.
100 means 0.01 ohm it will give.
Yes, 0.0.
So 0.01 means okay, no? Short.
Yeah, sir. Yes.
Yeah,
Thank you, sir.
yeah.
Hello, sir. Good evening, sir.
Yes.
Sir, op-amp draws no current. It will be applicable in for VCVS and VCCS, right, sir?
Yes.
So for CCCS and CCVS, the op-amp draws current.
No. For there are two circuits there. One is open loop, the other one is closed loop.
Yes, sir.
Open loop op amp will never draw current. After you give feedback, you can have 4 types of feedback. One is for VCVS, which is series shunt.
Yes, sir.
CCVS, shunt series. VCCS, series. CCVS, shunt. So there will be 4 types of feedback. I will explain this in feedback amplifier.
So
But
for open loop, draws no
never draw current.
okay, sir.
Okay.
Sir, in 30F, sir. Today's class 30F.
30F. Yeah.
Sir, here you took 100 ohm at the output. You are placed at the bridge middle, sir.
That is connected. The other end is connected to ground, no?
Sir, here ground is 0 volt, sir. But the other end also you took 0 volt, sir. Between there is a resistor, sir. How you took 0 volt other side?
According to Ohm's law, if current has to flow, there has to be potential difference.
Yes, sir.
So Ohm's law says that I equal to V1 minus V2 by R.
Yes, sir.
V1 is 0, V2 is 0. 0 minus 0 by 100.
Sir, I understood that, sir. Why other end you should take? Why other end you are taken 0 volt, sir? Right side.
That one. If this end is 0, if you go up, it is 0.7 plus 0.7. If you come down, it is 0.7 minus 0.7 is 0.
I didn't get, sir.
Okay, this is 0, no? What is this Vx and what is Vy? Tell me.
Vx minus Vy.
Vx equal to 0 plus 0.7.
Yes, sir.
Vy equal to Vx minus 0.7.
Yes.
It is already 0.7. 0.7 minus 0.7 is 0.
0. Okay, okay, sir.
If you go up, you will add. If you come down, you will subtract. No?
Yes, sir. Sir, another doubt, sir. Sir, yesterday you solved one problem, civil service exam. Sir, there you are taken 500 millivolt, na, sir.
50 millivolt.
Sir, for the diode to be on, we should take 0.7 volt, na, sir.
Yes.
But they mentioned 0.5 volt. So in that case, diode will be off, na, sir.
Yes, it is off if it is piecewise linear. If the diode characteristics is straight line,
yes,
then
sir.
it is off, 0 current. But this is non-linear, no? Some current is going to flow, no?
No, yes, sir.
See, the characteristics is like this. So here some current is there.
Yes,
but
sir.
the characteristics is like this. Then if you give this here, it is 0 only.
Okay.
0 current.
So for linear it is 0, for non-linear there would be a current.
For piecewise linear it is 0. For non-linear some current is there. Some small current will flow.
Okay, sir. Thank you, sir.
Yeah.
Hello, sir.
Yes.
Sir, 33F, today's last part B, once you explain.
Tell me.
Yes, sir, part B, once you explain.
Part B. Yeah, what is your undistorted peak he is asking, no?
Yes, sir.
So your signal, your DC is at 5 volt.
Yes, sir.
So you need a waveform between 1.5 and 10.
Yes, sir.
Now you tell me what are the combination of waveforms that you want to draw? Suppose you want to draw some, see, I'm giving you one positive peak.
Same amplitude.
That's what I'm saying here. See, I'm giving you two lines. This is positive peak. This is negative peak. Am I right? Here we have DC. DC is 5. This is 10. This 1.5. Now, how many ways you can draw this signal? I'm telling you. You try to draw at home and see. If you draw any waveform other than what I have given, it will look very odd. Are you getting?
Yes, sir.
This is 5. This is 1.5. The best thing is you have to take up 3.5, down 3.5. That is the best thing. This is 3.5. This is 3.5. Then you will not have distortion. If you say, no, sir, I will take up to 5, then where is 5 at down? There is no 5. You cannot take. So 5 volt peak is wrong. Yes or no?
Yes, sir.
3.5 volt peak is right.
Okay. Sir, if diode is an amplifier.
Diode is not an amplifier. It is passive, no?
In some of the cases, diode will be amplifier, will change.
No. Diode is passive. It cannot work as an amplifier. It is only a switch.
Okay.
Hello,
Okay.
sir.
Yeah.
So just a small thing. We will be taking the linear part of BJT for doing amplification, right?
Yes. Small portion in the linear region.
Then why don't we directly take a resistor which acts as linear already?
Yes, you can take. The signal will get attenuated.
Okay.
Resistor, heat, no? It will generate heat.
Yes, sir.
The signal will come down. If you put 2 resistors, voltage division will be there. Already your signal is dead. If you give that dead signal to another 2 resistors, complete dead output you will get.
Okay, sir.
But yes, it is a linear operation. That means if you give sine wave, you will get sine only. But a dead input to a resistor, another dead sine wave you will get. Very small one will come.
Okay, sir. Clear, sir. Thank you.
Yeah.
Hello, sir.
Yes.
Sir, in the unstable state in monostable multivibrator, that can you please explain in when trigger is given?
When trigger is given, what will happen if the trigger is given? Which page is that?
15F, sir.
15,
Yes, sir.
So once you push the trigger for a short duration, what is V1? V1 is 0, no?
Sir, we'll calculate V1 across R2, no, sir?
Yeah. But this point is pulled up to ground, no? Across R2 there will be 0.
Okay.
Because this is ground. This node is also 0. Complete VSAT will appear across R1.
Complete VSAT. Okay.
That is your doubt, huh?
No, sir. Then that
Then
going.
once that is 0, V2 is at 0.7. Who is more? 0.7 is greater than 0.
Yes, sir.
Minus voltage, if it is greater than plus voltage, then output will go from plus VSAT to minus VSAT.
Plus VSAT to minus VSAT.
Because minus voltage is more than plus voltage.
Minus voltage is more than V minus.
Who is minus voltage? Minus voltage is at 0.7.
7.
Greater. So
yes, sir.
First, we will start from beginning. That is better. First,
no, sir.
In the beginning, the output is at plus VSAT. Then, if the output is at plus VSAT, this voltage will be at 5. We'll start from here. This is at plus 10. This is at 5. Can you see?
Yes, sir.
Then, with 10, the diode is on. You will have 0.7 here.
But, yes.
is greater than 0.7. V is positive. Then output continues to be at 10. This stable state. So first we should know that this is the state. Are you getting? What is the state? Output is at
10 volt.
V1 is at 5. Diode is on because of 10. There is 0.7 here. 5 minus 0.7, 4.3 volt VD is there, positive. Output is still at 10. Output will never change. From morning till evening, if you keep on seeing this circuit, V1 will be 5, 5, 5, 5. V2 will be 0.7, 0.7, 0.7. V0 will be plus 10, plus 10, plus 10. That is why we call this state as what state?
Stable state.
State. Now we want to change this state from plus 10 to minus 10. That means VD should be negative. Now you will start realizing how VD will be negative. If VD has to be negative, minus voltage should be more. Then what we thought, okay, we will decrease plus voltage to 0. That is the only way. Minus voltage is already at 0.7. So we will decrease the plus voltage to 0. So then we close the switch with a capacitor and ground. 0 is there, 0.7 is there, VD negative. Output switched from plus VSAT to minus VSAT. And after that, now it is your stable multivibrator operation. Now diode is off, so capacitor will charge. Capacitor will charge in negative. Once that voltage goes less than minus 5, this is minus 5, this is minus 5.1 for minus 10 volt here. Then the difference again will become positive. Output will go from minus to plus, that's all.
Okay, sir.
Okay.
Now it's okay, sir. Thank you.
Hello.
Yes.
Sir, for amplification purpose, we have an op-amp. Then why we need a small signal analysis of diode BJT MOSFET to use as an amplifier?
I have not got your question. First BJTs have come, no? Once op-amp is itself designed with BJTs.
Okay, okay, sir.
Yes or no? So if you see what is the internal structure of op-amp, you will have 40 BJTs biased at an operating point.
Okay.
So biasing is there even inside an op-amp.
Okay, already in their op-amp.
Yeah, when you are designing, suppose you know biasing of BJT and MOSFET, then you can design a good op-amp with that.
Okay, sir. Okay, okay. Thank you.
Hello? Hello?
Yes.
Yes, sir. In that Smith trigger, when source is given to non-inverting terminal, then I didn't get how VT is equal
Your
to...
voice is low.
Hello?
Yes.
Is it audible?
Yeah, yeah.
So I'm telling that in Smith's trigger, when source is given to positive non-inverting terminal, I didn't get how VT came that minus R2 by R1 we said, or plus R2 by R1 we said. Hello?
So the middle voltage, it has to cross 0, no? The middle voltage is there. One end is at 0, no? You are asking in a split trigger, this end is at ground. How this end is greater than 0 and less than 0, no?
No, sir.
Yes or no?
No, sir.
Here we have this resistors.
Yes, sir.
Huh? Yes or no?
Hello?
So this end should be greater than 0 or less than 0. That means this end should be lesser than minus R2 VSAT by R1 or greater than R2 VSAT by R1. For this point to go above 0 or below 0 to change the state from plus VSAT to minus VSAT.
Oh, means we are, how we are getting this minus R2 VSAT by R1?
See, in a series circuit, same current will flow. That is very important. Yes or no? The current through R1 and the current through R2 should be same. Yeah. Now, if I want this middle point to go just above 0, here I am having 1K or here I am having 2K, here I am having 1K. I'll take this as R1, this as R2. Now, suppose if R1 is say 2K and R2 is 1K. what I'm trying to say is, if this is 10, how much current is going to flow here? Tell me.
10 by 3.
This is 0, middle.
Yeah, 10 by 2, 5.
10 minus 0 by 2. How much? 5 milliamp. No?
Yes, sir.
Yes or no?
Yes, sir.
For the same 5 milliamp to flow here, what I'm saying is this should be minus 10 into 2K R2. R2 is 1K by 2K, I'm saying. How much is this? This is minus 5 volt.
Yes, sir.
Now calculate the current I. 0 minus of minus 5 by 1K. Is it not 5 milli?
Sir.
Yes, sir?
Here you're not applying that voltage division and all.
Here, no, I'm saying if this current and this current should be same, it should be middle. If the voltage at this point should have a ratio R2 by R1. That we have got from that KVL. I'm applying simple logic and telling you. KCL I've already applied. You can see VSAT minus 0 by R1. Or else you do one thing. You put 0 here because anyhow it is going to cross 0. VSAT minus 0 by R1 equal to 0 minus V in by R2, no?
Yes, sir.
From here, what is V in? It is minus R2 VSAT by R1, no? Yes, sir?
Yes, sir, I got it.
Yeah.
So then one more doubt means if in a diode, if it that V, VT and eta all will be given, then we have to consider that it is working in non-linear.
Yes, yes.
Otherwise, in general, it is piecewise linear.
Yes. VD on 0.7, then it is piecewise linear. But if the signal applied is 2 sin t, 3 sin t, 4 sin t, 5 sin t, then it is what you call rectification. But if the signal is 2 sin omega t millivolt, then it is small signal analysis. If the signal is in millivolt, can the diode be on? No, is it not? So a small signal, if it gives, there has to be DC also in series. Then it is small signal analysis.
Thank you.
Yeah. Okay, shall we stop? If you have any doubts, you can WhatsApp. Yes or no?